Hello there, and welcome to Physics with William, where curiosity gets a quieter seat, science slows its breathing a little, and large questions are allowed to unfold without anyone banging a spoon on the table, demanding the answer in 30 seconds. Tonight we're turning our attention to something so small that no one has ever seen it directly with their own eyes, and yet so important that nearly every object around you depends on it. The walls around you, the air nearby, the cup on the table, the screen in front of you, your hands, your heartbeat, your own place in the room at this very moment, all owe something to this tiny resident of the universe. We are going to ask a question that sounds simple at first and then becomes less simple the longer you sit with it. What is a proton really made of? It is the sort of question that can sneak up on you. You hear the word proton in school, nod politely, and place it somewhere in the mental drawer marked science things. It sits there beside atom, electron, nucleus, and perhaps a vague memory of diagrams with neat little circles and coloured dots, arranged as if the universe had been assembled by a very organised bead enthusiast. For many of us, that is where the proton stays, a little positive particle in the middle of the atom, a tiny chunk of matter, a building block, job done, mystery solved, time for lunch. But physics, with its usual lack of respect for tidy first impressions, does not leave it there, because the closer we look, the stranger that apparently modest little object becomes. A proton is not just a tiny hard ball tucked inside atoms like a pea inside a pod. It is not a miniature marble. It is not a simple speck waiting patiently at the centre of matter. It is busy. It is structured. It is dynamic in a way that would have startled earlier generations of scientists and would probably still startle most of us if we stopped to think about it while stirring tea or waiting for the kettle. Inside what seems like a single particle there is motion, tension, exchange, confinement, and a kind of constant internal activity that makes the word made almost feel too calm for what is going on. And that word made is doing a lot of work here, is it not? We ask what something is made of because we are used to ordinary objects. A chair is made of wood or metal. A loaf is made of flour and water and patience. A watch is made of gears and springs or batteries and circuits and occasionally frustration. Our minds like layers. We take something apart and expect to find smaller pieces that sit inside it in a reasonably cooperative fashion. We're comfortable with the idea that if we keep opening boxes, eventually we will reach the smallest box, and in that final box there will be one neat answer waiting for us with decent handwriting. The proton does not quite behave like that. Before we get into the details though, let me ask you something I always enjoy wondering about in these slower conversations. Where are you listening from tonight? Are you in bed already with the lights low and the day almost packed away? Are you in a kitchen after midnight with the hum of the refrigerator doing its loyal background work? Are you on a sofa, on a train, in a quiet room somewhere while rain touches the window, or perhaps under a blanket convinced you will stay awake for the science, and then promptly betrayed by your own circadian rhythm? And what time is it where you are right now? It feels oddly fitting, does it not, to be talking about the ingredients of matter while people scattered across different cities and time zones arrive together at the same question from their own small corner of the earth. If this kind of slow, scientific wandering is your cup of tea, and if you find it soothing, interesting, or simply a pleasant way to ease the mind after a long day, I would be very grateful if you gave the video a like and perhaps subscribed as well. It helps this little corner of calm find other people who also enjoy letting physics be something you can live with for a while rather than sprint past. And now, with that settled, let us turn to our very small subject and begin where most good confusions begin, with something that once looked obvious. If you had asked a person a little over 100 years ago what matter was made of at the deepest level, you would have received an answer that sounded quite firm for the time. Atoms, they might say. Atoms were once imagined as the indivisible units of matter, the final bits beyond which there was no smaller structure worth speaking of. The word itself comes from a notion of uncuttable things, pieces so basic they could not be divided further. It was a bold and elegant idea. Matter seemed complicated around us, but perhaps underneath all that complexity there were tiny enduring units, each kind with its own character, combining in different ways to produce the world. Then science did what science does when it is at its best. It kept asking whether the tidy answer was actually true, and so the atom, which had once been the end of the story, became the beginning of a new one. Electrons were found, the nucleus was uncovered. The atom turned out not to be a featureless little lump at all, but a system with structure. Suddenly there were parts within what had been called indivisible. Then even the nucleus, which sounded sturdy enough to be trusted for a while, turned out not to be a single thing either. It contained protons and neutrons. New layers appeared. New questions opened. The supposedly final box had another lid inside it. The proton arrived in this history first as a victory for simplification. Here, at last, was one of the basic inhabitants of the atomic nucleus. It had electric charge, mass, stability, and a clear role in the architecture of ordinary matter. It seemed dependable. If atoms were the elements of chemistry, then protons helped determine which element an atom was. Change the number of protons in a nucleus, and you do not merely alter a detail, you change the identity of the atom itself. 1 proton gives you hydrogen, 6 gives you carbon, 8 gives you oxygen. Enough of them, arranged in the right nuclei with neutrons alongside, and you have the ingredients for stars, oceans, lungs, stones, bread, bones, and conversations like this one. The proton was not some minor extra. It was central. So naturally people began to wonder whether the proton itself was truly elementary or only another waypoint on the road. That question did not arise because scientists were bored and felt like making things difficult for themselves. It arose because nature kept giving hints that the proton might not be as simple as it looked. In the middle decades of the 20th century, particle physics underwent one of its great periods of unruly expansion. New particles were being discovered in experiments with cosmic rays and accelerators. The tidy family portrait of matter was turning into a very crowded reunion. There were too many particles, too many resonances, too many patterns that looked meaningful, but were not immediately understood. The proton was part of this growing zoo, and physicists began searching for deeper order beneath the apparent chaos. Now, when ordinary people hear that a proton is made of smaller constituents, there is a natural temptation to imagine a tiny little solar system, or a set of peas in a pod or beads on a string. We reach for familiar shapes because our brains evolved in a world of apples, chairs, shoes, and badly folded laundry, not in the domain of quantum fields and confined particles. But the closer physics gets to the proton, the less useful those household pictures become. Something is inside, certainly. There is structure, there are constituents. Yet what those words mean down there is not quite what they mean in the kitchen or the garage. The proton is not a hollow shell with a few neat objects rattling around inside like forgotten screws in a biscuit tin. The difficulty begins with size, though even saying size is already slightly misleading. A proton is tiny beyond ordinary intuition. Not merely small in the way dust is small, but so far below the scale of sight and touch that language itself starts borrowing metaphors and hoping for the best. If an atom were enlarged to a scale we could walk through, the proton would still be a minute central resident compared with the full spread of the atomic cloud. Yet for all its smallness, the proton carries substantial mass compared with the electron. That fact alone should make us pause. The electron is also treated as fundamental in the standard picture of particle physics, but the proton is much heavier. Why? If it is made of smaller ingredients, where does all that heft come from? Is it simply the mass of the ingredients added together, the way a sack of potatoes weighs as much as the potatoes put into it? Or is something subtler at work? By the time we ask that question, we are already slipping beyond the schoolbook image and toward the real puzzle. There is something almost mischievous about the proton from a teaching point of view. At first, it seems like one of the easier particles to explain because it belongs to familiar matter. It sits in every atomic nucleus except the simplest hydrogen. when that hydrogen happens to have only one proton and no neutron. It is part of you, part of stone, part of water, part of ancient stars whose ashes ended up in the earth and eventually in your bones. It sounds comforting, familiar, domestic even. A particle you might trust to remember your umbrella and show up on time. Then you begin to inspect it. And this is where the quiet trouble starts, because the proton is not only made of smaller ingredients, it is also a place where some of the deepest ideas in modern physics meet. Quantum theory lives here. The strong interaction lives here. The story of mass lives here. The problem of how nature binds things together lives here. Even the question of what we mean by a particle begins to wobble slightly once we peer closely enough. In ordinary language, a particle sounds like a tiny object with a fixed identity, a little thing being itself in a little place. In high-energy physics, that word survives, but it carries more nuance than everyday speech suggests. A proton is a particle, yes, but also a quantum object with internal structure, fluctuating activity, and constituents whose behaviour cannot be pictured as tiny billiard balls politely keeping their distance. All of that may sound like the setup to something impossibly technical, the sort of topic that requires 7 blackboards and a deeply committed eyebrow. But the surprising thing is that the core idea can be approached quite gently. At first glance, one might expect the question, what is a proton really made of, to have a short answer? Quarks, someone says, and perhaps they say it with the confident air of a person who believes the matter is now closed. And in one sense, that answer is right. A proton is associated with 3 quarks in a particular arrangement known as 2 up quarks and 1 down quark. If all you want is the first layer of modern particle physics, that is the headline. It is clear, concise, and not wrong. It is also not the whole truth, because those quarks are not sitting there alone like 3 passengers on a quiet bench. They are held together by gluons, the carriers of the strong interaction, and those gluons are not merely passive glue in the everyday sense of the word. They are active participants in the proton internal life. They carry energy and momentum. They can produce further particle activity in the quantum vacuum. The inside of the proton is not static. It is more like a ceaselessly busy system whose measurable properties arise from the interactions of its contents rather than from a simple inventory list. So even before we properly introduce quarks and gluons in detail, it helps to clear away one misleading expectation. We are not travelling toward a tiny mechanical clockwork. We are travelling toward a domain where the distinction between object and activity becomes less sharp than common sense would like. The proton has identifiable features. It has charge. It has spin. It has mass. It can be measured and scattered and studied in exquisitely precise experiments. Yet what it is, at a deep level, is tied inseparably to what is happening inside it all the time. In that sense, the proton is not only made of things, it is made of relationships, exchanges, fields, and motion. That last point is one of the reasons physicists became so fascinated by it. There is a broad philosophical temptation when looking for the foundations of reality to imagine ever smaller little pebbles, as though truth must eventually reduce to a set of perfectly simple objects. But modern physics keeps complicating that urge. Sometimes the basic description of nature is not a pile of tiny Lego bricks. Sometimes it is a set of fields, symmetries, interactions, and allowed patterns of behaviour. Sometimes what looks like a thing is, on closer inspection, a stable form of activity. The proton fits into that more modern way of thinking. It persists, it can be counted, it travels through the world. But its persistence does not come from being a dead little lump. It comes from the fact that nature allows a certain kind of structured, bound, durable quantum state. That may sound slightly grander than intended, so let us bring it back down to earth. Imagine asking what a whirlpool is made of. Water, certainly, but not in the same way a brick is made of clay. A whirlpool is also a pattern, a sustained structure in motion. Stop the motion, and the thing itself is gone, even though the water remains. The proton is not literally a whirlpool, of course. and one should be careful with analogies before they start thinking too highly of themselves, but the comparison helps a little. The proton is not just ingredients packed together, it is also a stable pattern allowed by the rules of the quantum world. The more carefully physicists probed protons, the clearer it became that simple pictures were inadequate. High-energy experiments did something rather remarkable. Instead of merely observing protons from a respectful distance, researchers hurled particles at them with tremendous energy and studied how those collisions unfolded. It was a bit like trying to learn how a clock is built by firing very tiny projectiles at it and analysing the debris, which admittedly is not how one should investigate actual clocks at home. Yet in the world of particle physics, such collisions reveal structure. They showed that the proton contains smaller point-like constituents. The evidence accumulated, patterns emerged. The Quark model gained power. Quantum chromodynamics, the theory describing the strong interaction, rose to explain how those constituents behave, and then, true to form, the answer became richer instead of simpler. Because once quarks entered the story, physicists found that the proton cannot be understood by picturing only 3 of them, and then going home pleased with a job well done. There is also a sea of transient quark and antiquark pairs. There is the behaviour of gluons. There is the strange fact that most of the proton mass does not come directly from the masses of the quarks themselves. There is the question of how the proton spin is distributed among its internal components. There are puzzles still under investigation even now, despite how long the proton has been studied. One of the most familiar particles in the universe remains in some respects not fully settled in our understanding. I think that is part of what makes it such a satisfying topic for a quiet, long-form discussion. It has the right kind of scientific personality, familiar enough to feel relevant, strange enough to stay interesting, foundational enough to matter, subtle enough to resist oversimplification. If someone asked what dragons are made of, that would certainly be imaginative. But the proton has an advantage. It is real, common, and sitting quietly inside the atoms of the world, while also being a gateway to some of the most advanced experimental and theoretical work in physics. There is also something pleasantly humbling about it. We human beings are very good at living among things we do not truly understand. We hold mugs, breathe air, build cities, write laws, send messages, fall in love, misplace keys, and generally conduct our lives atop layers of physical reality whose deeper workings remain hidden unless we go looking. The proton is one of those hidden residents. It does its work without announcement. It helps make ordinary matter possible. It never asks for applause. And only when we turn our attention inward, past chemistry and atoms and nuclei, do we meet the fact that one of nature's most familiar particles is, in truth, a remarkably complex quantum system. So as we settle into this topic properly, it helps to keep both sides in view. On the one hand, the proton is deeply ordinary. It is part of the common material world. On the other hand, it is a site of profound physical subtlety. To ask what it is made of is not merely to list components. It is to ask what counts as a component in the first place, how binding works at the most intense scales, why mass exists in the proportions we observe, and what kind of language best describes something that is neither a tiny solid bead nor a loose collection of independent parts. That is where we are heading. But before we get to quarks themselves, before gluons arrive and make everything more interesting and less intuitive, it is worth pausing with the older picture for just a little longer, because for a surprising stretch of scientific history, the proton seemed far more straightforward than it does now, almost as though nature had offered a simple answer first and only later admitted there was quite a bit more going on under the surface. For a long time, the proton seemed like one of the easier residents of the universe to talk about. Not easy in the sense that anyone could hold one in their hand or inspect it under a lamp, of course, but easy by the standards of physics, which has a habit of turning even the most innocent-looking nouns into long discussions involving caveats, revised diagrams, and a scientist somewhere in history realizing with mounting concern that the simple story no longer works. Compared with light, gravity, or the strange behaviour of quantum particles, the proton once looked dependable. It lived in the nucleus. It carried positive charge. It had a certain mass. It helped define the identity of elements. That sounded wonderfully solid. A neat little occupant of matter, a small serious particle doing its job without fuss. And that first impression was not foolish. It came from real progress, hard-won and experimentally earned. Before physicists could even begin asking what a proton might be made of, they had to discover that atoms themselves were not the unstructured little units they had once been imagined to be. That realization took time, patience, and a willingness to stop trusting models that were starting to creak under the weight of evidence. In the late 19th and early 20th centuries, the atom was still changing shape in the scientific imagination. At first, it had been treated almost like a final dot, a minimal unit of matter. Then electrons appeared in the story, and the atom was forced open. Suddenly there was internal structure. There were parts. The door to deeper questions had been unlocked, and physics, once invited in, had no intention of leaving the furniture untouched. One of the great turning points came with the work of Ernest Rutherford and the famous scattering experiments that revealed the existence of the atomic nucleus. That discovery changed the physical picture dramatically. Instead of a spread-out soft cloud of positive matter with electrons embedded within it, the atom seemed to contain a tiny, dense central core. Most of the atom, surprisingly, was empty space, or at least empty in the everyday sense. Matter was not built like a pudding. It was built more like a tiny system with a concentrated centre and lighter inhabitants distributed around it. That centre, the nucleus, was astonishingly small compared with the full atom, yet it contained nearly all the mass. This was not a minor revision. It was a complete rearrangement of how matter was imagined. Once the nucleus had entered the picture, the next question was unavoidable. What exactly was inside it? The answer emerged gradually. The hydrogen nucleus, being the simplest of them all, was especially important. Hydrogen was not merely the lightest element in the periodic table. Its nucleus seemed to consist of a single positively charged entity, and that entity took on an outsized importance. It was identified as the proton. From there it became natural to think of the proton as one of the foundational constituents of atomic nuclei more generally. Here was the basic positive unit, a kind of core particle, neat and unmistakable. If you place yourself in that period of physics, it is not hard to understand why the proton appeared so satisfying. Scientists were assembling a workable inventory of matter. The electron handled negative charge in the outer regions of the atom. The proton took care of positive charge in the nucleus. The masses roughly made sense. Chemistry could be tied to atomic number, which in turn depended on proton count. The periodic table, once a beautifully organised pattern awaiting explanation, now had a deeper physical basis. To know how many protons sat in the nucleus was to know what element you were dealing with. In that respect, the proton was not just another particle, it was a marker of identity. It told you whether a given atom was hydrogen, carbon, oxygen, iron, or gold. If a particle helps distinguish bread from bone, air from copper, and your own body from the page of a book, it earns a certain reputation. And yet, even in those earlier decades, the picture had loose threads. One issue was mass. At first, some scientists wondered whether nuclei might simply be collections of protons and electrons arranged in a compact bundle, since atoms overall were electrically neutral and clearly involved both positive and negative charges, but the details did not behave as neatly as hoped. There were problems with nuclear spin, problems with masses, and problems with how such a picture would actually hold together. The nucleus was proving more subtle than a mere stack of known ingredients. This is one of those moments that recurs often in science. The first tidy model gets you part of the way. It explains enough to be useful and enough to feel promising. Then nature, with calm persistence, begins pointing out the corners where the explanation fails. The discovery of the neutron in the early 1930s was a major correction. Suddenly the nucleus made better sense as a combination of protons and neutrons. Positive charge came from protons. Additional mass and nuclear stability could be accounted for with neutrons, which carried no electric charge. This helped explain isotopes as well, those versions of the same element that share the same number of protons but differ in the number of neutrons. Once again, the proton retained its place as something deeply central. Count the protons and you know the element. Count the neutrons too and you know which isotope you have. The atom had become more sophisticated, but the proton seemed, if anything, even more established. It was now one of the two principal residents of the nucleus, a role that made it feel sturdy and settled. At this stage, many educated people could have been forgiven for thinking the proton was more or less understood. Certainly there was still physics to do, there always is. But the proton itself looked fundamental in the practical sense. It had a fixed charge. It had a known mass relative to the electron. It seemed stable, very stable in fact. Electrons could be knocked about, atoms could be ionized, nuclei could transform in radioactive processes, but the proton itself had a strong air of permanence. It was part of the long-term architecture of ordinary matter. If you were looking for the universe to provide a reliable little constituent, the proton looked like a solid candidate. What made this impression so powerful was that it aligned beautifully with how humans prefer to think. We like our foundations simple. We want the deeper layer to be cleaner than the surface layer. If chemistry is varied and complicated, then perhaps atoms are simpler. If atoms contain parts, perhaps those parts are simpler still. One can almost feel the hope behind this habit of thought. Somewhere underneath all the mess, perhaps reality becomes neat. Perhaps the proton is one of the neat things, a compact positive nugget. Tiny, yes, but conceptually well behaved. There is also a visual reason the proton once seemed more straightforward than it now does. Early teaching models encouraged images of matter that were mechanical and spatially tidy. One drew atoms as little systems. One drew nuclei as compact clumps. The proton, if shown at all, was often represented by a small marked sphere or a symbol in the centre of the page. Such representations were useful, and remain useful at the right level. After all, education needs approximations. One cannot begin with the most refined picture every time any more than one teaches geography by starting with tectonic plate dynamics before mentioning countries. But the trouble with pedagogical simplification is that the mind can become attached to it. The convenient image starts to feel like the thing itself, so the proton inherited a kind of cartoon certainty. It became the little positive ball in the nucleus. Not literally a ball, perhaps, but close enough for classroom purposes, solid enough to imagine, limited enough to define. This mental image stayed with generations of students, and in many contexts it still functions reasonably well. If you're explaining the periodic table, basic atomic structure, or why hydrogen behaves differently from helium, the proton does not need to be more mysterious than that. A useful model earns its keep by not overcomplicating the task at hand, but physics is rarely content with a model merely because it is helpful. A good model must also survive scrutiny, and the proton, once brought under closer scrutiny, began to show signs that its apparent simplicity might be a surface effect rather than a deep truth. One important clue came from the behaviour of the proton in scattering experiments, and from the growing number of particles discovered in the middle of the 20th century. Particle physics entered a period that was at once exhilarating and slightly unruly. New particles appeared in experiments with such enthusiasm that the field began to feel less like a tidy family portrait and more like a drawer full of assorted cables, adapters, and mysterious objects you are sure must belong to something but cannot immediately identify. The proton still seemed central, but it was no longer alone in a cleanly minimal world. There were mesons, baryons, resonances, and an expanding catalogue of short-lived entities whose relationships needed explaining. The question was no longer only what particles exist. It became whether some of them might be built from something more basic. In that environment, The proton began to look less like a final ingredient and more like a member of a larger pattern. This shift did not happen overnight, and it did not begin with everyone calmly agreeing that old pictures should be replaced. Science seldom moves that politely. There were competing ideas, provisional schemes, and years of gradual clarification. But the underlying pressure was clear. Physicists wanted order beneath the growing zoo of hadrons, the family of particles that includes protons and neutrons. The proton was still familiar and stable, but familiarity does not guarantee fundamentality. A brick is familiar too, yet it is not a basic constituent of geology. Still, before the deeper picture fully arrived, the proton retained an odd kind of double identity in the scientific mind. On the one hand, it was clearly not as simple as once imagined. On the other hand, it remained one of the most practically important particles in all of physics. This made it tempting to treat it as basic in one context and suspiciously complicated in another. Even now, in casual conversation, people often speak of protons as though they were elementary. That is not because modern physics forgot the Quark model. It is because on the scales of chemistry, biology, and daily material life, the proton acts as a robust identifiable unit. It survives, it can be counted, it defines atoms. In many real-world applications, that is enough. A proton in your body behaves as a proton whether or not you are considering its internal structure while making breakfast. Yet this practical reliability may be exactly what made its deeper complexity so surprising. There is a kind of intuition that says if something is stable and common, it must be simple. A mayfly may be delicate and mysterious, but a stone seems plain. The proton tempts that same intuition. It is not rare, it is not fleeting. It is not an exotic particle that appears for a fraction of a second in a collider and vanishes before anyone can get too emotionally attached. It is one of the workhorses of ordinary matter. One expects a workhorse to be direct. One does not expect it to hide a storm of quantum activity under the saddle. Another reason the proton once looked well understood is that its measurable properties were so sharply defined. It had a known electric charge. Not approximately positive, but precisely positive in the amount that balances the electron charge in ordinary atoms. It had a measurable mass, much larger than the electron mass. It had magnetic properties. It had spin. It participated in nuclear structure in consistent ways. All of this gave physicists something reassuring. Even if the proton were not ultimately elementary, it still behaved as a well-characterized object. This is not trivial. In science, the ability to measure a thing reliably often produces a sense of familiarity long before deeper understanding catches up. There is an old comfort in naming and measuring. Once we know how much something weighs, how it responds to fields, how it scatters, and how long it lasts, we feel that we know it. And in one sense, we do know it better. But there is always the possibility that what we have learned is the public face of the object rather than its inner constitution. The proton wore a very consistent public face. That consistency helped conceal how much remained to be discovered. In retrospect, one can see that the early confidence in the proton as a simple building block was part of a larger pattern in physics. Each time a layer of matter is uncovered, there is a natural period during which its main components feel final. Atoms feel final until they reveal electrons and nuclei. Nuclei feel final until they reveal protons and neutrons. Protons and neutrons feel final until signs of deeper structure accumulate. This does not mean science is always wrong. It means science moves by stages of adequacy. A model can be correct enough to transform understanding, while still incomplete in what it says about deeper levels. The proton as a basic nuclear constituent was not a mistake. It was a successful truth within a certain range of questions, and that range was extensive. Nuclear physics developed around protons and neutrons with tremendous success. Astrophysics relies on the behavior of protons in stars. Chemistry depends on proton count in nuclei. Even biology, though it seldom pauses to admire the fact, rests on atomic identities set by proton numbers. In that sense, the proton we thought we knew was not an illusion. It was a useful physical reality. The trouble is only that it was not the whole story. The shift from seeing the proton as simple to seeing it as internally structured did more than add one extra fact to a textbook. It changed the kind of language physicists had to use. Once a particle is no longer elementary, one must ask not only what pieces it contains, but how those pieces are held together, why they cannot easily be separated, how the observed properties arise from the internal dynamics, and whether the word piece itself still means what common sense thinks it means. That last question matters. In the everyday world, if something is made of parts, one can usually take it apart. A watch can be opened, a cake can be sliced, a chair can be dismantled, though the results may test your faith in instruction manuals. But protons do not surrender their inner constituents in such a straightforward way. Their internal structure would turn out to be real, yet not accessible in the usual physical sense of simply prying the thing open and removing the contents one by one. This is where the old image of the proton begins to falter most dramatically. A tiny solid object could in principle be broken into smaller tiny solid objects. But the proton is governed by the strong interaction, and that interaction behaves in ways that do not fit ordinary mechanical expectations. The deeper scientists went, the less the proton resembled a miniature pebble, and the more it resembled a bound quantum system whose stability depended on very specific rules. Those rules allow the proton to exist as a durable, identifiable particle, but they do not allow its internal constituents to wander freely in the way marbles might roll out of a broken bag. Even so, before that deeper insight was established, there was a long period in which the proton occupied a comfortable place in the hierarchy of matter. It was the positive anchor in the nucleus. It was the count that defined the element. It was the heavy partner to the electron. It was, in the minds of many, one of the final little residents of physical reality. That image lingered because it works so well for so much of science. If you are balancing chemical reactions, studying radioactivity, classifying elements, or explaining why the sun shines through nuclear fusion, the proton did not need to be anything more than what it appeared to be. A stable positive particle with a crucial role in matter. Full stop. Only when physicists started asking more aggressive questions did the proton begin to feel less settled. What happens if we probe it at higher and higher energies? Does it scatter as though it has internal points of concentration? Why do families of particles seem to fall into patterns that suggest a substructure? How should we understand the growing population of hadrons without drowning in an ever-expanding list of separate ingredients? Those questions push the proton out of its comfortable role as an apparently final building block and into a new light, one in which its simplicity looked increasingly like an approximation. That is often how reality introduces its deeper layers. It does not begin by announcing them. It allows a useful picture to do its work for years, sometimes decades, and only then, when experiments become precise enough or questions become sharp enough, does it reveal that the tidy object at the center of your diagram is not wrong but incomplete. The proton was one of those objects, one of the particles we thought we knew, a positive kernel in the nucleus, a dependable constituent of matter, a familiar unit in the architecture of the world. And all the while, beneath that familiarity, there was more going on than the old picture had room to say. Once that possibility is admitted, the whole tone of the subject changes a little. The proton no longer looks like the end of the reductionist journey. It looks like another doorway. A stable doorway, yes, a very important one, but still a doorway into a stranger interior, where the language of little lumps starts to fail, and the story of what matter is made of becomes less about tiny solid pieces and more about how the quantum world allows structure, motion, confinement and identity to emerge together inside something that had once seemed almost simple enough to draw as a dot. When most of us first learn about matter, we inherit a very understandable habit of imagination. We picture things as made of smaller things, and those smaller things as little solid pieces. Sand is made of grains, flour is made of fine particles, A wall is made of bricks. A loaf is made of ingredients. If someone keeps asking what something is made of, the mind naturally keeps shrinking the pieces while preserving the same basic idea. Smaller bits become tinier bits, then tinier still, until eventually one imagines the smallest possible pieces of reality as little hard specks, compact and self-contained, each one sitting there being itself in a neat and respectable way. It is a very human way to think, and for a while it can be surprisingly useful, but it becomes much less reliable once physics starts examining matter at truly small scales, and few examples show that more clearly than the proton. The proton has had a long career in the scientific imagination as a particle that sounded almost comfortingly concrete. Positive charge, stable, located in the nucleus, more substantial than the electron, essential to atomic identity. It felt like the sort of thing that should be easy to picture. Even if one admitted that it was far too small to see, it still seemed natural to imagine it as a tiny compact object, something like a bead of positivity sitting at the heart of matter. Not a literal bead, of course, but bead-like enough for the imagination to stay happy. That picture survives in many school diagrams because it serves a purpose. If you're trying to explain why atoms differ from one another, why nuclei carry positive charge, or why hydrogen is simpler than oxygen, a small symbolic dot works very well. The trouble begins only when that symbolic dot is mistaken for an accurate mental portrait. Because a proton is not really a tiny hard pellet in the way common sense wants it to be. It is not like a grain of dust made ridiculously small. It is not like a seed, a pebble, or a microscopic ball bearing. It does not have the kind of surface, interior, and quiet self-possession that belong to ordinary objects. Once physics learned how to probe matter with much greater resolution, the proton stopped looking like a simple thing and started looking like a deeply active quantum system. That shift, from solid spec to quantum mystery, was not just a matter of updating a diagram. It changed what kind of explanation was even possible. Part of the difficulty is that our everyday intuition is built on a scale where solidity feels real and obvious. You touch a table and it resists your hand. You knock on wood and it answers back with firmness. You drop a spoon and it clatters rather than dissolves into a philosophical debate. At the scale of daily life, things occupy places, keep their shapes, and behave as though they're made of substantial stuff. We're trained by experience to trust that impression, so when we start asking about the constituents of matter, we carry that trust with us. We assume that deeper down there must be smaller versions of the same kind of reality. Solid things made of even smaller solid things. Yet modern physics keeps spoiling that comfortable inheritance. What it finds instead is that the microscopic world is governed by quantum principles that do not fit neatly into everyday categories. At that level, particles are not little billiard balls quietly waiting to be arranged. They have wave-like aspects. They are described by probabilities and quantum states. Their behavior depends on interactions that cannot always be pictured as mechanical pushing and pulling in the old classical sense. They can be localized in some experiments and spread out in others. They can behave as though they are discrete things, and yet not possess the kind of sharply defined trajectories that everyday objects have. If this sounds like the universe refusing to sit still for its portrait, that is not entirely unfair. The proton is one of the clearest places where this quantum strangeness collides with our older mechanical instincts. At first, it was tempting to think of it as one of the final sturdy units of matter. Then evidence began to show that it had internal structure, and once internal structure appeared, the old intuition returned immediately. Very well, people thought. Then perhaps the proton is like a tiny container holding even tinier objects inside it. Perhaps there are little subparticles tucked in there like peas in a pod. But that picture, while not completely useless as a first stepping stone, also turns out to be deeply misleading. To see why, it helps to think about what it even means to look inside something in physics. In the ordinary world, looking inside is straightforward. You cut open an orange, You unscrew the back of a clock. You unzip a bag. The inside is simply revealed because the thing occupies space in a familiar way, and its parts retain their ordinary identities when separated. A clock taken apart gives you gears and springs. A sandwich taken apart gives you bread, filling, and perhaps an unhelpful amount of mayonnaise. The whole can be decomposed into parts that make sense both inside and outside the system. The proton does not offer itself to inspection like that. There is no tiny knife one can use, no delicate lid to lift, no miniature maintenance hatch marked internal components. Physicists had to learn about its structure indirectly, by scattering other particles off it at high energy and studying the results. This is a much stranger way of investigating something than taking it apart on a workbench, but it is one of the few options available when the object in question is both extraordinarily small and governed by quantum laws. What emerged from those scattering experiments was not the image of a calm little sphere with neatly arranged contents. It was evidence for point-like constituents, yes, but also evidence for a much more dynamic and complicated interior than any classical miniature machine could capture. This is the point where the proton begins to leave the world of ordinary objects behind. If you ask what it is made of, the answer cannot be given in purely material terms the way one describes a cake or a chair. It involves constituents, certainly, but also fields, interactions, confinement, and ceaseless internal exchange. The proton is not just a bag of ingredients. It is a stable quantum state maintained by the strong interaction, one of the fundamental interactions of nature. That interaction is not merely a background force tugging on the parts. It is central to what the proton is. Even before one introduces quarks by name, this is worth dwelling on for a moment. In daily life, structure is usually more passive. A house stays together because nails, beams, bricks, and gravity arrange themselves in a workable architecture. There is interaction there, obviously, but one can still speak of the parts as though they have their own independent existence and have simply been assembled. In the proton, the interaction is so strong and so essential that the identity of the whole cannot be cleanly separated from the behaviour of what is inside. The constituents are not lounging around in there waiting to be counted like apples in a basket. They exist as part of a profoundly active bound system. That word bound matters. The proton is not a random cluster. It is not a passing fluctuation that just happens to hold together for a moment. It is stable on timescales that are, for ordinary purposes, effectively eternal. Protons are among the durable residents of the material universe. Some speculative theories allow for proton decay on fantastically long timescales, but no convincing evidence has ever shown ordinary protons to fall apart in any accessible span of time. For chemistry, for stars, for rocks, for oceans, for lungs, for every ordinary act of living, the proton is stable. That stability once encouraged the idea that it must therefore be simple, but in physics, stability does not always arise from simplicity. Sometimes it arises from a particularly robust pattern of quantum behaviour. A useful comparison, though not a perfect one, comes from thinking about music rather than objects. A musical note played by an instrument is not a solid thing, yet it can be stable, recognisable and repeatable. Its identity comes from pattern and structure, not from being a tiny hard object. The proton is not music, of course, and one should not get too sentimental about analogies before they begin expecting royalties, but the comparison hints at something important. A physical system can be real, measurable and stable, without being well described as a static little nugget. The proton belongs more to that kind of reality than the older image of a tiny bead would suggest. As quantum theory became unavoidable in describing the microscopic world, the language of matter itself began to change. Instead of asking only where a particle is and what it is made of, physicists had to ask how it is described by a quantum state, how it interacts, what symmetries constrain it, and how its observed properties emerge from those rules. The proton sits right at the meeting point of that transition. It is made of constituents, yes, but its mass, spin, size, and other measurable properties are not simply the straightforward sum of tiny separate objects with labels attached. They emerge from the quantum dynamics of the whole system. This is where the old idea of solidity becomes especially slippery. What does it mean to say something is solid when, at deeper scales, the familiar notion of little chunks of matter occupying sharply bounded places gives way to excitations, fields, and probabilities? In ordinary life, solidity is a useful macroscopic phenomenon. Tables feel solid. Walls feel solid. A closed door feels impressively committed to remaining a door when you walk into it half asleep. But that solidity is an emergent experience. It arises from electromagnetic interactions, quantum exclusion principles, and the collective behavior of matter. It is not because the particles inside are tiny pebbles packed together like gravel in a sack. So when we imagine the proton as a solid speck, we are importing a macroscopic feeling into a domain where it no longer belongs. The proton has size in a measurable sense. It has internal structure in a measurable sense. But it is not solid in the household meaning of the word. There is no tiny hard shell. There are no tiny rigid walls. There is instead a cloud of quantum activity governed by the strong interaction, with constituents that are confined in a way that resists ordinary picturing. And here another subtlety appears. When people hear that the proton has internal constituents, they often imagine the mystery has been reduced. Very well, they think. The proton is complicated, but at least now we know it is built from simpler ingredients. Problem solved. Yet quantum physics rarely lets the story end there. The deeper structure is not merely smaller stuff in a smaller box. It is a new kind of description. The ontology itself shifts a little. You do not simply go from one size of marbles to an even tinier size of marbles. You go from ordinary objects to quantum entities whose behavior is described by rules that challenge classical intuition at almost every turn. That is why the proton became such a rich object of study in the 20th century and remains one today. It sits in ordinary matter and yet refuses to be understood in ordinary terms. It belongs to the nucleus of every atom you know, and yet the theory required to describe its inner life is one of the most mathematically sophisticated in all of physics. It is familiar and alien at the same time. A proton in your body is doing exactly what protons do everywhere, but what it is doing is not especially well captured by the image of a tiny positive pebble. The journey from that pebble image to the modern picture involved more than improved experiments. It required a change in mindset. Classical physics had trained people to think in terms of definite objects with definite states. Quantum physics teaches, more cautiously, that what can be said depends on what is measured, how it is measured, and what theory connects those measurements. The proton therefore became less like a visible thing hidden at a tiny scale, and more like a system whose nature is revealed through patterns in experiment and theory together. You do not see the proton interior directly. You infer it. You reconstruct it. You learn its structure from what happens when other particles collide with it, from how momentum is distributed, from how scattering rates behave, from how bound states of quarks and gluons are described within the framework of quantum chromodynamics. That last phrase may sound forbidding, but its basic role is simple enough to state. It is the theory of the strong interaction, the interaction that governs the behavior of quarks and gluons and thereby the inner life of protons and neutrons. It is one of the great achievements of modern physics. Yet for all its success, it does not restore common sense. It replaces one kind of clarity with a deeper, stranger one. The proton becomes understandable in principle through this theory, but not picturable in the old schoolbook way. There is a charming irony in this. The more carefully physics understands the proton, the harder it becomes to explain using everyday metaphors. Early on, when understanding was limited, the proton seemed easy to picture. Later, when understanding deepened, the picture became harder, not easier. This happens often in science. The simplest image is not always the truest one. Reality at the deepest levels may be more elegant mathematically, while also being less hospitable to the imagination trained by tables, apples, raincoats, and staircases. One of the most important consequences of this shift is that the proton can no longer be thought of as merely containing its ingredients the way a bowl contains fruit. Its constituents are inseparable from the fields and interactions that bind them. Energy itself plays a central role. Motion plays a central role. The very vacuum around and within the proton is not empty in the old classical sense, but alive with quantum possibility. This is a long way from the original notion of a tiny compact positive sphere. The proton is not less real because of that. It is more subtle. And that subtlety matters because it changes how we think about matter more broadly. The proton is one of the main ingredients of atomic nuclei, so understanding it means revising our idea of what ordinary stuff is. It means that the solid world is built from atoms, atoms from nuclei and electrons, nuclei partly from protons, and protons from a quantum drama that resists being translated back into little mechanical bits. The floor beneath your feet is not just solid because it contains solid little seeds of matter all the way down. It is solid because the quantum world, through several layers of structure, produces macroscopic behavior that feels stable and resistant at our scale. This is one of the reasons particle physics can feel both remote and oddly intimate. The objects it studies are unimaginably small and described by theories that can seem forbidding. Yet those objects are not irrelevant curiosities. They are the hidden architecture of the ordinary. The proton is part of the common material world, but it teaches a profoundly uncommon lesson. The deeper you go, the less the universe resembles the tidy mechanical furniture of common sense. Even the word particle becomes less straightforward under pressure. In ordinary language, a particle suggests a tiny crumb, a minute fragment of substance. In modern physics, the term survives for historical and practical reasons, but it carries more theoretical weight and less everyday comfort. A proton is a particle, yes, but also a bound state. A quark is a particle, yes, but not one you ever find wandering freely in isolation. A gluon is a particle in one sense, and also an excitation of a field in another. The vocabulary remains familiar while the concepts underneath it grow much stranger. This can make physics sound as though it is changing its mind every few decades. But what is really happening is refinement. The old words are kept because abandoning them entirely would create chaos, but the theories gradually teach us not to trust the everyday associations attached to them. So when the proton moved from being treated as a solid speck to being studied as a quantum system, physics was not merely adding detail, it was crossing a conceptual border. On one side lay the comfortable world of little pieces, each one an object in the plain mechanical sense. On the other side lay the quantum domain, where identity, structure, and behavior are inseparable from interactions and probabilities. The proton did not vanish in that transition. It remained real, stable, and measurable. But it became mysterious in a more interesting way. Not mysterious because nothing could be known, but mysterious because what could be known no longer fit the habits of intuition that had shaped earlier pictures. And perhaps that is the healthiest kind of scientific mystery. Not ignorance dressed up dramatically, but understanding that keeps opening onto deeper questions. The proton still carries its positive charge. It still anchors nuclei. It still helps define every element in the periodic table. Those older truths remain intact, but beneath them lies a world where the proton is less like a tiny object and more like a carefully organized quantum storm, a durable pattern of confined constituents and energetic exchange that only looks simple from far away. Once that is admitted, the next step becomes unavoidable. Because if the proton is not a basic solid speck after all, then we have to ask what those hidden constituents are and how they manage to produce something so stable, so ordinary in our daily lives, and yet so strange when viewed up close. By the time physicists began to suspect that the proton was not a simple indivisible particle after all, they were already deep into one of the most dramatic periods in the history of modern science. The old tidy picture of matter had begun to splinter into something much busier. New particles kept appearing in experiments. Some lived briefly and vanished. Some seemed related to others in puzzling ways. Some could be grouped into families that looked suggestive but not yet fully explained. It was as if nature had opened a cupboard that scientists had assumed contained a few well-labelled jars, only to reveal shelf after shelf of unfamiliar objects, many of them rattling, glowing, or refusing to sit still long enough to be catalogued properly. In that crowded and slightly unruly landscape, the proton remained one of the familiar figures. It was stable, it was common, it was part of ordinary matter. It was not some fleeting curiosity glimpsed for an instant in a cloud chamber, yet even the proton began to look less isolated than it once had. Physicists started to notice patterns among the many strongly interacting particles that suggested a hidden order. The proton, the neutron, and a wider family of hadrons seemed too structured, too related, too mathematically tidy in their grouping to be mere accidents. Something more basic appeared to be sitting beneath them. Now, when science starts to suspect that apparently different things may be built from a smaller set of deeper ingredients, there is usually a mix of excitement and caution. Excitement because hidden simplicity is one of the great pleasures of physics. Caution because nature has a tendency to reward clever guesses only after first embarrassing them in public. Still, the idea began to take hold that the proton might be made of more fundamental entities, and that these entities might also explain the wider hadron family. This was not just about opening one particular particle and peering inside. It was about uncovering a new layer of reality that could make sense of a whole region of particle physics at once. That is where quarks entered the story. The name itself has always had a certain charm. Many scientific terms sound as if they were assembled by a committee, trying not to get too emotional. Quark sounds different. Slightly whimsical, slightly improbable, a word that feels as though it arrived with one eyebrow raised. And yet behind that unusual name lay a serious and powerful idea. Physicists proposed that many hadrons, including protons and neutrons, could be understood as combinations of more fundamental constituents. These constituents came in different types, or flavours as physicists rather cheerfully call them, and by arranging them in the right combinations one could explain the patterns seen in experiments. For the proton, the proposed composition was especially elegant. It could be described in terms of 3 quarks, not 3 identical ones, but 3 in a specific combination, 2 of one kind called up quarks, and 1 of another kind called a down quark. That combination gave the proton the right electric charge and placed it naturally within the emerging theoretical framework. The neutron, meanwhile, could be described by a closely related arrangement, with 1 up quark and 2 down quarks. It was an appealing step. The proton and neutron, so central to the nucleus and so similar in many ways, could now be understood as siblings, built from the same basic ingredients in slightly different arrangements. This was a major conceptual shift. The proton was no longer a final building block. It was itself a composite object, a bound state of smaller constituents. Yet the transition was not as simple as replacing one tiny ball with 3 tinier balls and calling it a day. Physics almost never rewards that sort of easy translation from old imagery to new. The quarks were not little peas tucked inside a pod. They were quantum entities, and their role inside the proton could not be understood in ordinary mechanical terms. The quark model opened the door, but the room beyond it was far stranger than a first glance suggested. At first, though, even the basic idea was bold enough. If quarks were real constituents, where were they? Why had no one seen one by itself? Why had experiments not simply plucked a quark out of a proton and displayed it like a tiny trophy? These questions did not invalidate the model, but they did give it an unusual character. Unlike electrons, which can exist freely and be detected on their own, quarks refused to appear in isolation. They behaved as though they were permanently confined inside composite particles. That made them rather peculiar citizens of the microscopic world. The proton seemed to be built from quarks, but quarks were never found wandering around on their own like loose screws on the floor of a workshop. That oddity alone should tell you something important about the proton. Whatever is going on inside it is not a scaled-down version of ordinary assembly. If a watch is made of gears, You can remove a gear and place it on the table. If soup is made of vegetables, you can fish out a carrot with a spoon if you're determined enough. But if the proton is made of quarks, those quarks are not available in the same way. Their existence is tied to a regime of physics governed by the strong interaction, and that interaction behaves in a way profoundly unlike the familiar forces of everyday experience. Even so, the quark model quickly showed its strength. It brought order to what had looked like a chaotic population of particles. Hadrons that once seemed like an untidy zoo could now be grouped in a more systematic way. The proton fit beautifully into the scheme, the neutron fit too. Other particles found their places. Suddenly, there was a sense that the proton inner life was not merely hypothetical ornamentation, but part of a broader organizing principle. The stage had been set, and quarks had taken it with surprising authority. Still, it is worth lingering on the word inside, because it is both helpful and treacherous. To say quarks are inside the proton gives the right first impression. It signals that the proton is not elementary, and that it contains identifiable constituents. But the everyday meaning of inside can mislead us if we let it. In common life, what is inside something usually occupies a smaller region, enclosed by a stable boundary. The ingredients are there first, then the container is there around them, and all of it can be imagined in the geometry of familiar objects. The proton does not quite behave like that. It has a measurable size, yes. It has internal structure, yes. But quarks are not little beads resting quietly in an empty pocket at its centre. Their existence inside the proton is part of a dynamic quantum system, where motion, confinement, and exchange are all ongoing. If you try to imagine three quarks orbiting one another like tiny planets, the picture becomes too classical too quickly. If you imagine them fixed in place like raisins in a bun, the picture becomes too static. If you imagine them bouncing off the walls of a miniature box, the picture becomes too mechanical. Each image catches a fragment of something useful and then overreaches. The real description belongs to quantum field theory, not household intuition. The quarks inside a proton are better thought of as constituents within a bound quantum state, distributed and interacting according to rules that do not translate neatly into little moving marbles. That may sound unhelpfully abstract, but the point becomes clearer if we remember that the proton is not just made of quarks. It is made of quarks under the governance of the strong interaction. And this interaction does not merely hold them together the way glue holds pieces of paper. It shapes the very possibility of the proton as a stable object. The quarks do not just happen to be close, they are confined. Their behaviour is linked to the exchange of gluons, the carriers of the strong interaction, and this makes the proton a deeply active system. Even the apparently simple statement that the proton contains 2 up quarks and 1 down quark is only the beginning of the story. Before we widen the picture though, it helps to appreciate just how conceptually important those up and down quarks were. Physics had found a way to understand familiar nuclear matter in terms of deeper constituents, but not by descending into an endless chaotic multiplication of parts. On the contrary, quarks reduced complexity. The proton and neutron no longer needed to be treated as utterly separate kinds of basic matter. They could be understood as related composites. This is one of the marks of a good scientific advance. It does not merely add detail, it makes diverse phenomena appear as variations on a more unified theme. There is also something quietly satisfying about the proton being built from a combination that is both simple and subtle. 2 up quarks and 1 down quark. That sounds almost modest when said plainly. But those few words represent a major shift in what we take matter to be. No longer a world built out of visible-style miniature solids, but a world in which the familiar massive particles of the nucleus are themselves composite quantum systems built from constituents that cannot be isolated. The proton remained part of ordinary matter, yet its ordinariness now rested on much deeper strangeness. As experiments improved, the evidence for internal proton structure became more compelling. High-energy scattering experiments were especially important here. Instead of merely treating the proton as a featureless target, physicists used very energetic particles to probe it on smaller and smaller scales. The results indicated that within the proton there were point-like constituents carrying fractions of its momentum. This was exactly the kind of behaviour one would expect if the proton were not a smooth, indivisible object, but a structured system. The data did not simply flatter the quark idea politely, they gave it real experimental bite. Even so, the language of fractions introduced another feature that made quarks feel unlike ordinary parts. The quarks inside the proton seemed to carry only some of its total momentum in scattering experiments, not all of it. This meant that even once quarks had taken the stage, they were not alone in the performance. Something else was helping hold the proton together and helping account for its observed properties. That something else would become increasingly important, and it would complicate any attempt to picture the proton as a mere trio of ingredients. But before we get there, notice what has already happened to the old image of matter. The proton, once treated as a final positive unit, has become a composite object. The constituents of that object are quarks. These quarks come in different kinds. They combine in specific ways. They cannot be found freely. Their behaviour is governed by a strong interaction unlike anything in everyday experience. And the proton is no longer merely a thing. It is a state, a bound configuration of quarks and the fields that govern them. The stage picture becomes more and more crowded, but also more coherent. There is a temptation when learning this material to cling to the phrase made of as though it guarantees a familiar kind of explanation. If a proton is made of quarks, then surely the quarks are the real thing, and the proton is just a package. But physics is subtler than that. The proton is real in its own right. It is not an illusion produced by quarks in the dismissive sense. It is a stable composite particle whose identity matters at the scale of nuclei, atoms, chemistry, and stars. The fact that it has internal constituents does not demote it to a mere convenience. It simply places it at a different level in the hierarchy of matter, and that hierarchy is not a set of boxes inside boxes in the old mechanical sense. It is more like a sequence of increasingly fundamental descriptions, each one appropriate to certain scales and questions. A chemist can speak of atoms and molecules without mentioning quarks. A nuclear physicist can speak of protons and neutrons without always needing to compute every underlying quark interaction from scratch. A particle physicist, however, goes deeper and asks how those protons and neutrons themselves arise. Each layer is real within its proper domain. The proton occupies a wonderfully interesting place because it is both a familiar effective unit and a composite object with hidden inner structure. Quarks therefore changed not just what physicists said about protons, but how they thought about physical explanation more broadly. Instead of imagining the world as built from little durable nuggets whose identities are simple all the way down, one had to allow for a reality in which what looks elementary at one level may emerge from a more fundamental theory beneath it. This does not make the upper level false, it makes it contextual. The proton in your body is a proton in every meaningful sense. Yet from the deeper perspective of particle physics, it is also a bound state of quarks and gluons. That word gluons has been waiting rather patiently at the edge of the stage, and it deserves a proper entrance soon. For now, though, it is enough to say that quarks alone do not tell the full proton story. The proton is not just three named constituents in a quiet arrangement. It is an energetic quantum environment in which those constituents are constantly interacting. Their confinement and the exchange processes binding them are not optional details. They are essential. Without them, there is no proton in the form we know. There is also something philosophically interesting about the quark picture. Quarks are among the deepest constituents in our current standard description of matter, yet they are never directly encountered in isolation. So the proton, an ordinary constituent of nuclei, is built from entities that do not show up by themselves in ordinary experience or even in high-energy experiments as free particles. That is a lovely inversion of common sense. The familiar thing is made of hidden constituents that nature refuses to present one by one. It is as though the universe has agreed to reveal the ingredients list, but not let you remove the ingredients from the recipe. That refusal turns out not to be a temporary inconvenience, but a profound feature of the strong interaction. Quarks are confined in such a way that attempts to separate them do not simply liberate a lone quark. Instead, the energy involved can produce new bound particles. This keeps the quarks from ever stepping onto the stage alone. They appear only as members of hadrons, never as solitary performers. So when we say quarks take the stage, we mean they become central to the theoretical and experimental understanding of the proton. Not that they suddenly emerge for solo applause. Even their electric charges are peculiar by everyday standards. Quarks carry fractional electric charge, something unlike the charges of familiar particles such as the electron or proton. That fact alone once sounded almost outrageous. Fractional charge does not show up in ordinary isolated matter, and yet within the quark model it fits beautifully. Combine 2 up quarks and 1 down quark, and the total gives the proton its full positive charge. The arithmetic works. The pattern is elegant. The hidden constituents have strange properties individually, yet together they produce the familiar particle long known in the nucleus. This is the sort of scientific development that feels almost literary in retrospect. A familiar figure is revealed to have a hidden cast within it. The proton, once imagined as a lone actor, turns out to be an ensemble. Quarks step forward first because they supply the basic constituent picture. They explain relationships among hadrons. They account for certain observed scattering behaviours. They provide the proton with a deeper internal identity. Yet from the beginning they also hint that the full story will be more complicated than any simple inventory can capture. That is why this part of the story is so important. Quarks do not just add detail to the proton. They change the kind of object the proton is understood to be. No longer a final indivisible particle, not merely a tiny positive dot, but a composite bound system built from more fundamental constituents whose existence is inseparable from the quantum rules governing their confinement and interaction. Once that door is open, one can never quite go back to the old image without feeling that it has become a costume rather than a body. Useful in the right setting, perhaps, but no longer convincing at close range. And so the proton interior begins to take shape, not as a static little chamber, but as a dynamic quantum structure whose main visible players are quarks. 2 up quarks and 1 down quark form the recognizable core of the description. Yet even as they step into the light, it becomes clear that they are not alone, and that what binds them together is no mere background detail, but the next essential part of the story. Once quarks enter the picture, the next question arrives almost immediately, and it is a very reasonable one. If the proton contains quarks, what exactly keeps them together? It is not enough to say that they are there. A structure is not explained simply by naming its ingredients. If someone tells you a bridge is made of steel, you still want to know how the steel is arranged, what holds the load, why the whole thing does not collapse into the river, and whether you should trust it enough to walk across while carrying groceries. The proton asks for the same kind of follow-up. Quarks may be the key constituents, but something must bind them into a stable particle, and that something turns out to be not merely important, but central to the entire story. This is where gluons step in. The name encourages a first impression that is not entirely wrong, but also not nearly complete enough. Gluon sounds like glue, and that is deliberate. Gluons are indeed associated with the strong interaction that binds quarks together inside protons and neutrons. If you want the quickest possible statement, you can say that gluons are the carriers of the strong force. They are what mediate the interaction among quarks. They help hold the proton together. All of that is true, and all of it is useful as a starting point, but the word glue can be misleading if it makes you picture something passive. Ordinary glue is a quiet helper. You spread it on one thing, press another thing against it, wait a little, and hope you have not attached your fingers to the table in the process. Once the bond forms, the glue mostly disappears from the story. It has done its job. It sits there and behaves. Gluons are not like that. They are not a sticky filler packed between quarks like paste between bits of cardboard. They're active quantum participants in the proton inner life. They carry energy, they carry momentum, they interact with quarks, but they also interact with one another. And that last fact changes everything. To appreciate why, it helps to compare the strong interaction with the electromagnetic interaction. Because electromagnetism is the force most people know a little about, even if only indirectly. Electricity, magnetism, light, the way charged particles interact. All of that belongs to the electromagnetic side of nature. In modern physics, the electromagnetic interaction is carried by particles called photons. Photons transmit the interaction between charged particles. An electron can interact with another electron through the exchange of photons. But photons themselves carry no electric charge, which means they do not directly tug on one another in the same way charged particles do. That makes electromagnetism subtle and rich, but still in a certain sense more straightforward than the strong interaction. Gluons are different. They carry the type of charge relevant to the strong interaction, a property known as color charge, which despite the name has nothing to do with visual color. No proton is secretly painted inside like a toy box. The term is just a label physicists use for a kind of charge associated with quarks and gluons in the theory of the strong interaction. Because gluons themselves carry this charge, they do not merely connect quarks like neutral messengers, they also interact among themselves. So the proton is not a quiet arrangement of quarks with a few neutral signals passing between them. It is a far more intensely self-interacting system, with gluons constantly participating in the internal dynamics. This makes the proton feel less like an object assembled from pieces and more like a tightly organised storm. The quarks are important, yes, but they are not alone at centre stage. Gluons fill the proton interior with exchange activity. They are part of the reason the strong interaction is so strong. They are part of the reason quarks remain confined. They are part of the reason the proton has the properties it does. If quarks are the obvious named ingredients, gluons are the restless infrastructure that makes the whole thing possible. There is something almost perverse, in the best scientific sense, about how the strong interaction behaves. At first you might think that if quarks are bound together, then pulling them apart should weaken the bond the way stretching a spring eventually loosens a grip, or the way distance reduces many familiar interactions. But the strong interaction does not reward that expectation. Within the proton, quarks can move around in complicated ways, yet trying to separate them does not simply free them. In fact, the interaction tends to resist separation more strongly as the quarks are pulled apart. That is one of the reasons quarks are never found alone in ordinary experiments. The energy you pump in by trying to isolate one does not produce a liberated quark waiting politely in the lab. Instead, that energy can create new hadrons, new bound particles, as though nature would rather manufacture additional company than let a single quark leave the party by itself. Gluons are deeply involved in that behaviour, because they interact with one another as well as with quarks. The field structure inside a proton is more complicated than a simple exchange picture might suggest. One can loosely think of the strong interaction as creating a kind of binding network that does not thin out into harmless weakness when stretched in the way common sense expects. This is why the proton is not just three quarks sitting together by good fortune. It is three valence quarks, meaning the quarks most directly associated with the proton identity, embedded in a sea of gluonic activity that helps define the proton as a stable bound state. That phrase valence quarks deserves a moment of attention because it quietly signals that the proton is already more than just three constituents. The two up quarks and one down quark are the leading actors in the sense that they account for the proton basic quantum numbers, including its electric charge. They are the main named residents. But the full proton is not exhausted by that list. Gluons contribute significantly to what is going on inside. In high-energy experiments, the proton often behaves like a complex system whose momentum is shared among quarks, gluons, and additional transient quark and antiquark pairs that arise from the quantum activity of the strong interaction. So even while we talk about the proton as two up quarks and one down quark, We must not imagine a quiet trio sitting in a clean room. The gluons ensure that the room itself is busy, crowded, and constantly changing. It is easy to underestimate how radical that is. In ordinary objects, what holds the parts together is usually not treated as a major constituent in its own right. If you describe a chair, you mention wood or metal, and maybe screws. You do not usually describe the electromagnetic forces between atoms as though they are active residents of the chair, even though at a deeper level they are essential. With the proton, however, the binding mechanism is not something you can comfortably leave in the footnotes. Gluons are not background bookkeeping. They are central to the proton structure. Much of what the proton is depends on them. This becomes especially important when we think about mass. Common sense says that if something is made of parts, its mass should mostly come from the masses of those parts added together. That works well enough for many everyday objects. The mass of a loaf comes from the mass of the ingredients, not from some dramatic extra contribution generated by the tension among the flour and water. But the proton does not follow that familiar script. The masses of the quarks inside it are only a small fraction of the proton total mass. Most of the proton mass comes instead from the energy associated with the strong interaction, including the motion of quarks and the gluonic fields binding the system together. In other words, gluons are not just the reason the proton stays whole. They are a major reason the proton weighs what it does. That is one of the most striking lessons in modern physics. Matter is not simply built by stacking the masses of tiny ingredients. Mass can emerge from energy, and binding in a much more substantial way than daily intuition would ever suggest. The proton, which helps make up the nuclei of ordinary atoms and therefore contributes enormously to the mass of visible matter in the universe, gets most of its mass not from heavy constituent quarks sitting inside it like dense little stones, but from the dynamic energy of the strong interaction. Gluons are at the heart of that. They help turn a small amount of quark mass into a much heavier composite particle by way of the intense energy bound up in the system. If that sounds almost unfair from the point of view of common sense, that is because it is. We are used to thinking that matter is made of stuff and that stuff has weight, because it is stuff. The proton teaches a more subtle lesson. The deep material world is not only about ingredients, it is about interactions. A great deal of what feels solid and substantial in the visible universe owes its existence to the energy of gluons and the strong interaction, rather than to the bare masses of quarks alone. There is another reason gluons make the proton difficult to picture. They do not sit still in any ordinary sense. In the quantum description, gluons are continually exchanged and continually contributing to the proton internal state. This does not mean that one should imagine little glowing packets flying back and forth like bees in a jar. That image quickly becomes too literal. But it does mean that the proton is a dynamic bound system rather than a frozen arrangement. Its constituents are described by quantum fields, and the gluonic activity is part of the ongoing structure. The proton is stable as a whole, yet internally it is busy. That combination of stability and internal motion is one of the most interesting features of the proton. We often think of stable things as static and dynamic things as unstable. A parked car is stable. A boiling pot is active. A proton manages to be both durable and internally energetic. It is a bound quantum state that persists across cosmic timescales in ordinary matter while containing ceaseless interaction within. This is one reason the storm analogy helps a little, provided one does not become too attached to it. A storm has organised motion. It is not random chaos, but neither is it static. The proton is similar in the sense that its identity comes from a structured pattern of activity, not from being a tiny rigid pellet. The gluons are also responsible for a phenomenon that makes the strong interaction especially unusual. At very short distances or very high energies, quarks can behave almost as though they are less tightly bound, a feature known as asymptotic freedom. The name sounds as though quarks are about to go on holiday, but the situation is subtler than that. Inside a proton, when quarks interact at extremely short range, the effective strength of the strong interaction can weaken. Yet at larger separations, the interaction does not fade away like an ordinary long-distance force. It becomes stronger in a way that contributes to confinement. This strange two-sided behaviour is part of what makes quantum chromodynamics, the theory of quarks and gluons, so remarkable. Gluons are central to both effects because their self-interaction shapes how the force behaves across scales. For the proton, this means there is no simple mechanical picture of quarks tied together by tiny strings in the everyday sense, even though string-like metaphors are sometimes used informally to convey confinement. The actual theory is a quantum field theory with rich behaviour, and gluons are not optional extras. They are woven into the very logic of why quarks cannot be isolated, and why the proton exists as a stable particle at all. Remove the gluonic interaction, and the proton does not merely weaken, it ceases to be the object we know. Experimental physics has had to become extremely clever to study these gluons, because one cannot simply open a proton and point at a gluon the way one points at a button on a coat. Instead, researchers infer gluonic contributions through scattering experiments, jet production in high-energy collisions, deep inelastic processes, and other elaborate measurements that reveal how momentum and energy are distributed among the proton constituents. Over time, one of the clear lessons has been that gluons carry a substantial share of the proton momentum, especially at high energies. This is another clue that the proton is not just its valence quarks. The gluons are not hidden support staff. They are major participants. There is something almost democratic about the proton once this becomes clear. The most visible identity markers come from the valence quarks, yes, but the actual internal economy of momentum and energy involves a wider cast, with gluons playing a huge role. It is rather like assuming a theatre production belongs entirely to the three actors whose names are on the poster, only to discover that the lighting crew, stage machinery, sound system, and half the building itself are part of what makes the performance what it is. The analogy is imperfect, as all analogies are once they start feeling too pleased with themselves, but the basic point stands. Gluons are not merely keeping the quarks from drifting apart, they are part of the proton ongoing physical identity. This also helps explain why describing the proton as made of three quarks, though not false, always feels incomplete to physicists. It is like calling a city three neighbourhoods and leaving out the roads, traffic, electrical grid, water system, and everyone who actually moves through it. The two up quarks and one down quark tell you something essential but not enough. The gluons create a far richer internal reality. They mediate the strong interaction. They contribute to the proton mass and momentum. They interact among themselves. They help generate the sea of additional transient quark and antiquark pairs that flicker in and out as part of the quantum structure. The proton, far from being a neat trio, is a whole miniature environment, and still, in a way, it works. That is perhaps the most striking thing. All this complexity yields something stable, common, and indispensable. The proton sits inside atomic nuclei without fanfare. Chemistry proceeds, stars burn, water exists, carbon exists, you exist. The intense quantum activity does not spill out into daily life as confusion, because the proton is such a robust bound state. Nature has found a way to make a durable constituent of matter from a system that is anything but quiet internally. Gluons are one of the main reasons that is possible. There is also a wider philosophical lesson here about what counts as holding something together. In ordinary thought, the binder is less important than the bound object. We focus on the bricks, not the forces that make the wall coherent. But in the proton, the distinction begins to blur. The gluons do not merely hold pre-existing matter together from the outside. Their activity is part of the constitution of the proton itself. The bound state is inseparable from the binding. That is a very different idea from the everyday picture of separate pieces assembled by some external adhesive. Once you see that, the proton becomes hard to trivialize. It is not just another particle. It is a concentrated lesson in how the deep universe works. A lesson that says structure comes from interaction. A lesson that says mass can emerge from energy. A a lesson that says stability can arise from internal motion rather than despite it, and a lesson that says the hidden architecture of ordinary matter depends not only on identifiable constituents like quarks, but on the restless gluonic fields that keep the whole arrangement alive. So the gluons do far more than hold the proton together in the casual sense of the phrase. They help create the conditions under which the proton exists as a stable, massive, observable particle. They give the strong interaction its peculiar power. They prevent quarks from roaming free. They contribute to the proton momentum and mass in fundamental ways. They interact among themselves, making the proton interior a self-coupled quantum system rather than a tidy box of ingredients. They are the reason the proton is not merely a little cluster, but a highly organized bound state built out of energy, confinement, and constant exchange. And once that activity is taken seriously, another layer of the story starts to emerge, because gluons do not simply bind the name quarks and stop there. Their presence makes the proton interior even busier than a three-constituent picture suggests, filling it with additional fleeting pairs and a deeper kind of internal crowding that takes us beyond the tidy first description and into the restless sea just beneath the surface. If the proton had turned out to be nothing more than three quarks held together by gluons, physics would still have had a remarkable story to tell. Even that stripped-down version would already be far stranger than the old image of a tiny solid speck. But nature, not for the first time, declined to stop at the tidy version. The deeper scientists looked, the more the proton began to resemble not a quiet trio in a neat arrangement, but a crowded and constantly shifting quantum environment. Beneath the simple statement that a proton contains two up quarks and one down quark lies a much livelier reality, one in which gluons can generate additional quark and antiquark pairs, momentum is shared among many participants, and the proton interior is better understood as a restless sea than a fixed little set of pieces. That sea is not made of water, of course, though the metaphor has earned its place because it captures something important. It suggests motion rather than stillness. It suggests a background that is not empty. It suggests that what looks calm from a distance may conceal ceaseless internal activity. All of that fits the proton surprisingly well. The proton keeps a stable identity as a whole, yet internally it is never truly quiet. The three valence quarks, the two up quarks and one down quark that give the proton its defining quantum numbers remain crucial. They are not dethroned by the fuller picture, but they are no longer alone on the stage. Around and among them there is a fluctuating population of gluons and transient quark and antiquark pairs, rising and fading as part of the proton quantum structure. This is one of those moments in physics where the ordinary language of parts and pieces starts to feel strained. If you ask what a loaf is made of, the answer sounds stable. Flour, water, yeast, salt. If you ask what a watch is made of, the answer sounds countable. Gears, springs, screws, casing. But the proton resists that kind of inventory. Its ingredients are real, yet some of them are present only as fleeting participants in a dynamic internal state. A proton is not a box with a fixed list of contents written neatly on the outside. It is more like a persistent quantum society, with permanent citizens and a busy stream of temporary visitors, all governed by the strong interaction. The sea quarks, as they are often called, are part of that shifting population. They are not the same as the valence quarks that define the proton basic identity. Instead, they arise from the restless activity of the gluon field inside the proton. Because gluons carry the kind of charge relevant to the strong interaction, and because they can interact among themselves, they can also produce quark and antiquark pairs. These pairs do not turn the proton into a different particle. They do not overwrite the fundamental role of the valence quarks. But they do mean that the proton interior is not just three quarks and some glue. It is a quantum state in which additional pairs can appear and disappear, as part of the ongoing dynamics. At first, that can sound almost like an accounting error. How can a proton still be a proton if extra quarks and antiquarks are popping in and out of the picture? Does this not ruin the clean statement that it has 2 up quarks and 1 down quark? The answer is no, because the valence quarks and the C quarks play different roles. The proton identity, its overall charge and related defining properties, comes from the valence structure. The additional pairs are produced in matched quark and antiquark combinations, so they do not alter the proton net quantum numbers in the same way. They enrich the interior without changing the basic identity of the whole. It is a bit like a city whose official population is defined by its permanent residents, while daily life also includes commuters, visitors, deliveries, temporary workers, and all the movement that makes the city function as a living place rather than a static census number. That is a helpful comparison because it keeps the balance right. The proton is not a random cloud where everything is equally important all the time. The valence quarks matter greatly, but neither is it a static trio. The C matters too because it contributes to the internal distribution of momentum, energy, and interaction. When high-energy experiments probe the proton, they do not always encounter only the valence quarks. Depending on the scale and the process, they can probe gluons and C quarks as well. In that sense, the proton is not just what it is in some timeless abstract definition. It is also what it reveals under investigation, and what it reveals is a far more populated interior than early pictures ever imagined. One of the reasons this became clear is that when scientists looked at how momentum is distributed inside the proton, the 3 valence quarks did not account for everything. A proton in motion carries momentum, of course, and one can ask how that momentum is shared among its constituents. If the proton were simply 3 quarks in quiet coexistence, one might expect those quarks to carry essentially all of it. But experiments showed that this is not the case. Gluons carry a substantial share of the proton momentum, and C quarks contribute as well. In some high-energy regimes, gluons become especially important. So the proton does not merely contain a hidden C in a poetic sense. That C has measurable physical consequences. It shows up in the data. It affects what happens in collisions. It shapes the proton behavior in ways that cannot be ignored. This is where the word surface in the chapter title becomes useful, provided we handle it carefully. The proton does not have a surface in the everyday sense, like the skin of an apple or the painted exterior of a chair. But it does have an outward simplicity that can mislead. From the outside, so to speak, it looks like a stable, positively charged particle, with a certain mass and a role in atomic nuclei. That is the surface level of description, the one that works well for chemistry and much of ordinary physics. Beneath that lies the quantum structure, and beneath that structure lies a constant internal bustle that makes the proton less like a bead and more like a living field configuration. Not alive in the biological sense, of course. No one need worry that their breakfast is quietly judging them at the proton level, but alive in the sense of ongoing activity, internal exchange, fluctuation, and dynamic pattern. This idea of fluctuation is one of the hardest things for common sense to welcome. Everyday objects are either there or not there. A spoon on the table does not flicker into a temporary spoon and back out again. A coat hook does not briefly generate a coat and an anti-coat when no one is watching. The quantum world, however, is less reserved. Quantum fields allow processes that do not resemble the fixed furniture of daily life. The proton interior reflects that. The C quarks are not separate little objects camped permanently in assigned seats. They are part of the fluctuating quantum environment created by the strong interaction. This does not make them unreal. On the contrary, their effects are real enough to be measured. It simply means that reality at this scale is not well described by static inventory. That distinction matters because it helps guard against a common misunderstanding. When people hear about C quarks and transient pairs, they sometimes imagine that the proton is becoming vague or fictional, as though physicists have stopped knowing what is in it and started waving their hands in the general direction of mystery. In fact, the opposite is true. The idea of the proton C arose because experiments became more refined and theory became more sophisticated. The picture grew more complex because the evidence required it. not because anyone fancied making the proton sound dramatic. If anything, the sea is a sign of progress. It reflects a deeper understanding of what the strong interaction actually does inside a bound state. There is also a deeper lesson here about emptiness. In everyday language, if something is not filled by permanent objects, we tend to call it empty. A room with no furniture is empty. A pocket with no coins is empty. But the proton, like the quantum vacuum more broadly, teaches that physical emptiness is not the same as everyday emptiness. Even the regions not occupied in any classical way by fixed constituents are not blank. They're governed by fields. They allow fluctuations. They sustain interaction. The space within the proton is not a little hollow chamber. It is a region of intense quantum activity, where gluons and transient pairs contribute to the whole. The sea image becomes even more useful when one thinks about scale. From far away, the ocean can look smooth and almost featureless. Stand on a cliff, and it presents itself as one broad surface. Get closer, and you begin to see waves, currents, foam, shifting patterns, and a kind of organized disorder. The proton is similar in that its identity as a single particle is perfectly real at one scale, yet when probed more deeply it reveals a much richer internal texture. The valence quarks are like the main landmarks, the features you can anchor the map around. The gluons and sea quarks are like the motion and weather and traffic of the place, the things that make it a living environment rather than a static structure. It is worth noting that this restless sea is not a small correction to an otherwise simple story. It influences major physical questions. It affects scattering probabilities in accelerator experiments. It affects how the proton behaves when smashed at high energies. It affects how we calculate processes involving hadrons. And it even contributes to ongoing puzzles about the proton properties, including questions about spin and internal distributions that scientists are still working to pin down with greater precision. The proton may be one of the oldest acquaintances in particle physics, but it has not run out of ways to surprise. One of the more subtle surprises is that the proton can contain not only up and down sea quarks, but heavier flavors in transient ways as well, depending on the energy scale being considered. The strong interaction allows a richness that goes beyond the minimal identity statement. This does not mean the proton secretly turns into a zoo every afternoon and back again by tea time. Its overall identity remains stable. But it does mean that the proton internal quantum state is capable of involving more than the three constituent names one learns first. The deeper picture is generous with participation, even if nature remains strict about what counts as the proton overall. Now, in saying all this, one must be careful not to imply that the proton is chaotic in a lawless way. Restless does not mean random without structure. The proton is described by a highly disciplined theory, quantum chromodynamics, and its internal sea is constrained by that theory. The fluctuations are not whimsical. The distributions are not arbitrary. There are rules, conservation laws, and measurable patterns. One of the great achievements of modern particle physics has been learning how to connect these deeply quantum descriptions to actual experimental data. That is no small feat, because the strong interaction becomes difficult to calculate directly in the low-energy bound state regime where protons live. The mathematics is demanding, the approximations delicate, and the need for computational methods enormous. Yet despite these challenges, a coherent picture has emerged. The proton is a bound state of valence quarks, immersed in gluonic activity and a sea of quark-antiquark pairs, all contributing to a composite object that is stable, measurable, and indispensable. The sea also changes how one thinks about the word constituent. The valence quarks are constituents in a straightforward sense. They are the quarks that define the proton main quantum character. But the sea quarks are constituents in a more conditional sense, because they are part of the proton internal state without being permanent defining markers of its identity. The gluons are also constituents in a crucial sense, even though introductory explanations sometimes treat them as mere messengers. The proton therefore teaches that constitution is not always a matter of a fixed shopping list. It can be a matter of ongoing participation in a stable quantum whole. This is a challenging thought if one is fond of simple material pictures. We like the idea that the world is built from neat little things that keep to themselves and simply stack upward into larger structures. The proton refuses that elegance. It insists that dynamic relation is as important as substance. It insists that what a thing is may depend not only on what permanent ingredients it contains, but on the energetic, fluctuating, field-governed processes that occur within it. In that sense, the proton is a very modern object. It belongs to a physics in which being and happening are no longer cleanly separable at the deepest level. And yet, despite all this inner motion, the proton remains stubbornly ordinary in its outward role. It stays in nuclei. It contributes to atomic mass. It defines elements by count. It persists across immense stretches of time. This contrast between internal turbulence and external stability is one of the most beautiful features of the subject. Nature has built one of the main components of visible matter not as a dead little pellet, but as a stable pattern of intense quantum activity. The calm object of chemistry is, in its inner life, a busy and fluctuating environment. There is a quiet irony here as well. The more science has learned about the proton, the less it resembles the kind of thing one would naturally imagine as the foundation of matter. If one were allowed to invent basic constituents using only common sense, one would probably choose simple hard units with crisp boundaries and permanent identities. Instead, the actual building blocks of the visible universe include objects like the proton, whose mass comes largely from interaction energy, whose constituents cannot be isolated, and whose interior contains a shifting sea generated by gluonic dynamics. It is a reminder that the universe is under no obligation to make its deepest levels feel comfortable to creatures accustomed to mugs, staircases, socks, and weather reports. Still, the sea picture is not merely humbling. It is also productive. It guides experimental design. It shapes theoretical work. It explains why high-energy collisions reveal so much more than a simple three-body interior would allow. And it prepares us for the next major lesson, which is that the proton internal crowding is not just a matter of complexity for its own sake. It is tied to one of the most distinctive features of the strong interaction, namely that quarks never emerge as free isolated particles. The sea is restless, yes, but it remains a sea within the proton and within other hadrons. Its inhabitants do not simply drift off into independent existence. There is a deeper reason for that, a reason rooted in confinement. And without that confinement, the proton would not merely look different. It would not be the stable particle the universe has relied on for so much of its visible matter. At this point in the journey, the proton has already lost the comfortable simplicity it once seemed to have. It is no longer a tiny positive pellet sitting quietly in the nucleus, like a well-behaved guest at the centre of the atom. It has become a bound quantum system made of quarks, filled with gluonic activity and surrounded by a restless internal sea. But there is one feature of this whole story that still feels especially strange, even by the standards of particle physics. If quarks are real constituents, why do we never see one on its own? Why has no one ever found a single free quark drifting through space the way electrons do? Why can we speak with confidence about quarks inside protons and neutrons, yet never catch one alone in a detector as a neatly isolated particle? That question is not a side issue. It goes right to the heart of what makes the strong interaction so different from the other fundamental interactions. It also changes how we think about the word made. If the proton is made of quarks, then common sense expects those quarks to be removable, at least in principle. A loaf is made of ingredients that can be separated. A machine is made of components that can be taken apart. Even atoms can lose electrons under the right conditions. But quarks behave differently. They are not just hard to isolate. Everything we know suggests that nature does not allow them to roam free at all. This property is known as confinement, and once you understand even the basic shape of it, the proton stops looking like a container and starts looking like something much deeper and more tightly organized. To see why confinement matters so much, it helps to begin with an instinctive expectation. In daily life, when two objects are bound together by some force, pulling them apart usually weakens the bond. Magnets stop attracting each other so strongly as you move them farther apart. A stretched rubber band resists, but eventually it snaps or releases. Gravity weakens with distance. Even electromagnetic attraction between charged particles becomes weaker as separation grows. We're used to the idea that distance dilutes influence. It feels like one of the most ordinary rules in the world. The strong interaction does not follow that rule in the way you would expect. At very short distances, quarks can behave almost as though they are less tightly constrained by the strong interaction. This is one of the reasons high-energy scattering experiments can probe their presence inside protons. But if you try to separate quarks farther and farther apart, the interaction does not simply fade into harmless weakness. Instead, the energy tied up in the strong interaction grows in a way that makes isolation harder, not easier. It is as though nature becomes increasingly unwilling to let the quarks part company. The farther you try to pull them apart, the more energy you pour into the system, and that energy does not usually buy you a free quark at the end of the effort. It buys you something else. What it buys you is new particles. This is one of the most counterintuitive features of the strong interaction, and it is why confinement feels so unlike anything in ordinary mechanics. If you pump enough energy into a proton in an attempt to tear quarks loose, the energy stored in the interaction can become great enough to create new quark and antiquark pairs. Instead of ending up with one lonely quark sitting on your laboratory bench, you end up with additional hadrons, new composite particles made from quarks that remain bound. Nature seems to prefer making more company, rather than allowing a single quark to leave by itself. It is a bit like trying to separate two dancers by pulling so hard that the dance floor itself produces extra dancers before either one gets away. The analogy is imperfect, but the basic idea is right. You do not get an isolated constituent. You get new bound systems. This means that when high-energy collisions break apart protons or other hadrons, the result is not the clean liberation of individual quarks. Instead, detectors see sprays of hadrons, often called jets, that reflect the underlying quark and gluon processes without ever revealing a quark as a free standalone object. The quarks leave signatures of their presence, certainly. Their momentum, their interactions, and their role in the collision can be inferred with great confidence. But they do not appear as lone particles the way an electron can. Confinement prevents that final step. There is something deeply important about this, because it tells us that quarks are not merely hidden by practical limitations. It is not as though physicists just need a slightly sharper microscope or a more patient attitude. The issue is structural. The theory itself says that quarks belong to a regime where isolated existence is not part of the physical story. They are fundamental in one sense, but not free in the way many other fundamental particles are free. That alone makes them unusual. Electrons can travel across empty space. Photons can stream from distant stars. Neutrinos pass through enormous amounts of matter with hardly any complaint at all. Quarks, by contrast, are always found bound inside hadrons. This does not make them fictional or second-rate. On the contrary, quarks are among the basic ingredients in the current standard description of matter. But their basicness comes with a condition. They are basic constituents that only show themselves inside composite particles. The proton therefore occupies a curious position in physics. It is a composite object, yet it is in some ways more directly accessible than the constituents from which it is built. That is a lovely reversal of everyday expectation. Usually one imagines that the parts are simpler and more available than the whole. In the case of quarks and protons, the whole is common and familiar, while the parts are permanently confined. A natural follow-up question is why the strong interaction behaves this way at all. Why should the force grow more resistant to separation instead of weakening with distance? The complete answer belongs to quantum chromodynamics. The theory of quarks and gluons, and the mathematics of that theory is not especially gentle. But the broad reason lies in the structure of the gluon field, and in the fact that gluons carry the very kind of charge associated with the strong interaction. Because gluons interact not only with quarks, but also with one another. The field lines do not spread out in the simple way electromagnetic influence often does. Instead, the interaction between quarks can be thought of, in a loose and limited way, as being concentrated into something more like a tube or string of field energy. As the quarks are pulled apart, the energy in that field configuration rises. Eventually it becomes energetically favourable to create new quark and antiquark pairs rather than allow indefinite stretching toward isolation. This picture is not exact in every detail, and one must be cautious with visual metaphors in particle physics, because they are always eager to overperform. Still, it helps convey why confinement is not just a brute rule pasted onto the theory. It grows out of the structure of the strong interaction itself. The proton is not a prison built around quarks by some external wall. The binding and the confinement are part of the same deep physical framework. Quarks are bound because the strong interaction behaves as it does, and because it behaves as it does, free quarks never emerge. That has consequences not only for what experiments see, but for the very meaning of internal structure. When we say the proton is made of quarks, we must not imagine the quarks as detachable little pieces in the usual sense. They are real constituents, yes, but constituents whose identity is inseparable from confinement. The proton is not like a bag of marbles, each marble retaining its independent status whether inside or outside the bag. It is more like a stable state of the strong interaction in which quarks are participants that cannot be abstracted into free objects without changing the physical situation completely. This is one reason the old image of matter as nested little solids becomes so misleading. Common sense likes to think that deeper structure means smaller and smaller stand-alone things. Break a rock into grains, grains into molecules, molecules into atoms, atoms into subatomic particles, and eventually one imagines you arrive at the smallest grains of all. But quarks refuse that grain-like dignity. They are not the final little pebbles waiting at the bottom of reductionism. They are quantum constituents whose existence is woven into a field theory that does not permit them to exist independently under ordinary conditions. The proton is therefore not just a shell around more basic matter. It is the condition under which a certain set of quarks can exist as part of a stable hadronic state. If that sounds almost philosophical, it is only because the physics itself pushes us there. Confinement forces a rethink of what it means for one thing to be made of another. In chemistry, composition is straightforward. Water is made of hydrogen and oxygen atoms, and those atoms can in principle be separated. A chair is made of wood, and the wood exists fine on its own. But a proton is made of quarks in a stronger and stranger sense. The quarks are not available as independent materials that can be extracted and laid out on a tray. They are constituents whose physical reality is always mediated by confinement. They are known through the roles they play inside bound states and through the signatures they leave in high-energy processes, not through direct isolated appearance. There is another reason this matters. Confinement helps explain why the visible world has the structure it does. Imagine a universe in which quarks could roam free easily. The entire architecture of matter would be different. Protons and neutrons might not be the stable, common building blocks they are. Atomic nuclei might not form in the same way. Chemistry as we know it might not exist. The strong interaction, by confining quarks into hadrons, helps create a world of durable composite particles that can go on to build nuclei, atoms, molecules, planets, oceans, and living organisms. Confinement is not a technical inconvenience at the edge of particle physics. It is part of the reason the ordinary material universe is possible in the form we know. It also adds a certain quiet irony to experimental particle physics. The more energy scientists use to probe quark behaviour, the more clearly the internal structure of hadrons can be inferred, and yet the particles doing the probing never quite get to pull a quark out into freedom. The experiments reveal deeper truth while also reaffirming the confinement principle. One learns more and more about quarks precisely by confronting the fact that they do not emerge alone. Their fingerprints are everywhere in the data, but the culprit never poses for a solo portrait. This can be frustrating at first if one has inherited the idea that science consists mainly of finding things and putting them in separate labelled containers. Much of science does work that way at a certain level, but modern physics often operates by inference, by pattern, by theoretical consistency tested against experiment. Quarks are among the best supported entities in all of particle physics, despite never being observed in isolation. Their charges, flavours, spins and interactions fit into a framework that explains an enormous amount of data. The proton behaviour in scattering experiments, the existence and classification of hadrons, the properties of jets in collisions, the success of quantum chromodynamics in describing strong interaction phenomena, all of this points to quarks with extraordinary strength. So confinement is not a sign that quarks are speculative in a weak sense. It is part of the physics that makes them what they are. One of the subtler lessons of confinement is that nature does not always divide its deepest ingredients according to our preferred visual categories. We like things that can be lined up, separated, and counted. A collection of apples behaves very nicely in that respect. So does a set of screws. You can separate them, store them, misplace one under the sofa, and still speak meaningfully of each item on its own. Quarks do not grant us that comfort. They exist in a theory that makes them fundamental, and yet denies them solitary appearance. The proton therefore becomes not just a composite object, but the proper habitat of its constituents. It is a place where quarks can participate in reality under the rules allowed by the strong interaction. That may be why confinement can feel almost biological in metaphor, though not in literal content. A fish can live in water but not on your kitchen counter for very long. A quark can exist in hadrons, but not as a free particle in the ordinary observable world. The analogy is only partial and should not be pushed too hard, but it captures the sense that context matters. The quark is not merely a thing hidden inside the proton. It is a constituent whose mode of existence is tied to a bound environment created by the strong interaction. And confinement is not the only unusual scale-dependent feature of the strong interaction. As mentioned earlier, quarks behave differently at very short distances where the interaction can become weaker. This phenomenon, known as asymptotic freedom, was one of the great theoretical discoveries that made quantum chromodynamics compelling. It explains why quarks inside a proton can sometimes appear almost free when probed at very high energies and very short ranges, even though they are never observed as free particles at larger separations. So the proton contains a remarkable duality. Deep inside, at very short scales, quarks can act with a degree of near independence. Try to pull them out into standalone existence, however, and confinement reasserts itself. The result is a particle whose constituents are both individually meaningful and permanently bound. This tension between near freedom and absolute confinement is one of the reasons the proton is such a rich object. It is not merely a cluster held together in a static way. It is a system governed by a force that changes character with scale. At one scale, quarks inside it can be treated as almost weakly interacting for certain calculations. At another scale, the same theory ensures that no quark will ever walk away on its own. That is a remarkable piece of natural design, if one may use that phrase cautiously. It gives the proton both internal structure and external integrity. Confinement also explains why the strong interaction does not behave like ordinary glue in another sense. Glue joins separate objects that could exist independently before and after the joining. You can have two pieces of wood before the glue, and two pieces after the glue fails. But quarks are not independent wood pieces awaiting adhesion. The strong interaction does not simply stick them together. It defines the conditions under which hadronic matter exists at all. The proton is not assembled from pre-existing free quarks, in the way a table is assembled from pre-cut boards. It is a bound state that emerges from the rules of quantum chromodynamics, and confinement is one of those rules. If one wanted to be especially careful, One could say that quarks never roam free because the universe, at least in the regime of ordinary low-energy hadronic matter, does not permit them to. Not because of a practical barrier, not because detectors are too weak, not because physicists have not yet tried hard enough, but because the strong interaction itself turns every serious attempt at isolation into the creation of new bound states. This makes free quarks not just elusive but absent as physical outcomes. The proton keeps its quarks, and if pushed hard enough it produces more hadrons rather than surrendering one. There is a certain elegance in that stubbornness. The same physics that makes the proton internally complex also makes it externally durable. Confinement is part of why the proton can serve as one of the long-term structural elements of matter. It is not merely held together by a strong bond, it is protected against constituent escape by a theory in which separation itself feeds the creation of new composites. The proton, in that sense, is not a fragile arrangement waiting to be peeled open. It is a robust solution to the equations of the strong interaction. And that robustness has another consequence. Because quarks remain confined, many of the familiar properties of the proton cannot be understood by imagining a simple count of little masses and little spins carried by three detachable parts. The whole system matters. The energy of confinement matters, the gluonic activity matters, the restless sea matters, what the proton weighs, how its momentum is shared, how its spin is distributed. All these questions depend on the collective behaviour of the bound state, not merely on a list of constituent names. Confinement, therefore, prepares the ground for one of the most surprising results of all, namely, that most of the proton mass does not come from the bare masses of its valence quarks, but from the dynamic energy of the bound system itself. One of the most surprising things about the proton is that if you ask where its mass really comes from, the first answer many people would give turns out to be badly incomplete. It is a very understandable first answer too. If something is made of smaller things, then surely its mass should come from the masses of those smaller things added together. That is how almost every ordinary object encourages us to think. A sack of potatoes weighs what the potatoes weigh. A bookshelf weighs what its wood and screws weigh. A bowl of fruit does not become much heavier because the apples are feeling energetic about being a bowl of fruit. In daily life, mass seems to belong mainly to ingredients. Put enough ingredients together and you get the total. The proton does not play by that rule in the way common sense expects. By now we know that the proton is associated with 3 valence quarks, 2 up quarks and 1 down quark, along with the gluons that bind them and the restless sea of additional transient pairs that churn within. So the obvious next move is to ask what those quarks weigh. Once you do that, however, a strange result appears. The bare masses of the quarks that define the proton are only a small fraction of the proton total mass. Add them together, and you do not get anywhere near the full heft of the proton, not even close in the everyday arithmetic sense, which means that the mass of one of the most familiar particles in ordinary matter does not mainly come from the simple masses of its named ingredients. That is not a technical footnote, it is one of the great conceptual lessons of modern physics. It means that when you hold an object in your hand, much of the mass in the ordinary visible matter around you is not there, because the fundamental constituents are individually heavy little grains. It is there because energy, motion, confinement, and interaction within particles like the proton generate mass in a much deeper way. A large share of the visible mass of the universe comes from the energy bound up in the strong interaction. The proton is one of the main places where that becomes true, and it changes the whole mood of the subject. Matter is not just weighty stuff stacked together. Matter gets much of its apparent solidity and heft from dynamics. There is a temptation to say that this is strange only because physics insist on making things sound dramatic. But it really is strange. If you had asked common sense to design the material world from scratch, it probably would have chosen elementary constituents with most of the mass built right into them. Tiny heavy bits making bigger heavy bits. That sounds efficient, respectable, and easy to explain to a sleepy student on a rainy Tuesday. Instead, nature built a world in which the proton, one of the principal sources of mass in atomic nuclei, owes most of its mass not to the simple sum of quark masses, but to the energy of quarks and gluons interacting in a confined quantum system. This is one of those points where physics becomes both more abstract and more intimate at the same time. More abstract because the explanation involves quantum chromodynamics, the strong interaction, and the relation between energy and mass. More intimate because it tells you something about the weight of the world around you. The chair, the cup, the page, the air, your own body, all of these inherit much of their mass through protons and neutrons in atomic nuclei, and those protons and neutrons derive most of their mass from internal energy. So the answer to where matter gets its heft is not simply from massive ingredients sitting there quietly, it is from activity. Bound, organised, intensely structured activity. At first that can feel as though the floor has moved slightly under the furniture. Part of the confusion comes from the way the word mass is used outside physics. In everyday speech, mass and weight blur together into one general sense of heaviness. In physics, mass has a more precise meaning, and one of the most famous lessons in modern science is that mass and energy are profoundly related. This is not just a slogan attached to nuclear power plants and science posters, it is a real structural fact about nature. A system can have mass because of the energy contained in it. The proton is one of the clearest and most important examples of this. Its mass reflects not just the bare masses of its quarks, but the kinetic energy of quark motion, the energy stored in gluon fields, and the intense binding dynamics of the strong interaction. A useful way to approach this without drowning in formalism is to think about a system rather than a mere collection. In daily life, when parts interact strongly, the whole can differ from the simple list of ingredients in meaningful ways. A stretched spring stores energy. A heated object contains more internal energy than a cold one. A compressed gas pushes back because of the motion and interaction of its particles. We're used to the idea that systems can contain energy beyond the rest identities of their parts. What we are not used to is the scale on which that becomes decisive inside the proton. There, the interaction energy is not a minor correction. It is the main event. This is one of the reasons the proton should not be imagined as a little box holding 3 tiny stones. If that were the case, then its mass would mostly be the mass of the stones. But the proton is not a box. It is a bound quantum state. The quarks inside it are moving. The gluons are active. The fields are intense. Confinement contributes essential structure. The whole system is saturated with energy, and because energy contributes to mass, the proton emerges as a much heavier object than a simple sum of bare quark masses would ever lead you to expect. There is a quiet elegance in that. It means that the world we experience as substantial is, in a deep sense, made substantial by relation and motion, not merely by little hard nuggets. A proton is not heavy because its quarks are individually very heavy. It is heavy because the strong interaction is so powerful, and because the quarks and gluons are locked into an intensely energetic bound state. The visible universe gets much of its ordinary mass from that deep internal struggle and balance. One can almost hear common sense objecting. Very well, it says, but where does that energy come from if not from the ingredients themselves? Surely energy cannot just appear as a sort of charitable donation from nowhere. And of course it does not. The energy is part of the physical system defined by the strong interaction. Quarks are confined. They cannot simply sit still as if resting in separate little compartments. Their motion contributes energy. The gluonic fields contribute energy. The act of binding itself, unlike the mild sort of binding in many macroscopic systems, is tied to enormous energy scales in the world of hadrons. The proton exists because nature allows this stable bound configuration, and that configuration has a mass corresponding to its total energy content. This is where the lesson becomes larger than the proton itself. One of the central achievements of 20th century physics was to show that mass is not always best thought of as a primitive property of little lumps of matter. Sometimes it is emergent. Sometimes it is what energy looks like when trapped or organized in a certain way. The proton is a brilliant example, because it is not exotic in the way a black hole is exotic. It is part of ordinary matter. It sits inside atomic nuclei all around us. So the fact that its mass is mostly generated dynamically means that much of the ordinary heft of the visible world is dynamically generated too. It also helps explain why the strong interaction matters so much for the architecture of reality. Electromagnetism shapes chemistry and everyday material behavior in enormous ways. Gravity shapes planets, stars, galaxies, and the large-scale structure of the cosmos. But the strong interaction, working inside hadrons and nuclei, is what gives protons and neutrons their existence and much of their mass. Without it, quarks would not be confined into these stable composite particles, and the familiar world of nuclei and atoms would not arise in anything like its present form. The mass of visible matter would be profoundly altered. The world would not simply be lighter, it would be different in structure from the ground up. There is a useful contrast here between the proton and the electron. The electron is treated in the standard framework as an elementary particle. It has a mass, and we do not describe that mass as arising from internal quark and gluon dynamics, because, as far as we know, there is no such substructure for the electron. The proton, by contrast, is composite. Its mass is mostly not the sum of the masses of its constituent valence quarks. That means the proton teaches a different lesson about matter than the electron does. The electron says some particles simply have their properties as elementary entities within the theory. The proton says other particles derive much of what they are from how more basic entities interact and bind. That distinction matters because it shows there is no single simple recipe for all mass in physics. Some masses are associated with elementary particles in one way. The mass of hadrons, like the proton, is generated largely through strong interaction dynamics in another. One must not flatten those into one story merely because the word mass appears in both places. The proton is telling us something very specific and very beautiful. Visible matter is heavy not mostly because quarks are heavy, but because the strong interaction makes bound states that carry immense energy as part of their very being. This also sheds light on why the proton is such a triumph of modern theory and computation. It is one thing to say in words that most of the proton mass comes from interaction energy. It is another thing to calculate hadronic properties from the underlying theory of quarks and gluons. Quantum chromodynamics is the governing framework here, but it is notoriously difficult to solve directly in the low-energy regime where protons live as bound states. The mathematics is not content to sit quietly and be friendly. It requires sophisticated techniques, approximations, and heavy computational work, especially in approaches where space-time is discretized on a lattice so the theory can be simulated numerically. Over time, those methods have shown with increasing power that the proton mass can indeed be understood as emerging from quark and gluon dynamics. In other words, this is not just a philosophical mood, it is a quantitative success of modern physics. That is one of the most satisfying parts of the story. The idea sounds almost poetic at first, that matter gets its mass from internal energy and confinement, but it is not poetry dressed up as science. It is science so deep that it briefly sounds poetic before the equations come in and remind everyone to sit up straight. The proton mass is not mysterious in the sense of being beyond calculation forever. It is difficult, but increasingly tractable. Physicists have not merely declared that energy is involved and wandered off for tea, they have built an entire theoretical apparatus to show how it happens. Still, from the human point of view, the conceptual shock remains. Imagine explaining to a younger version of ourselves that most of the mass in ordinary matter does not come from the masses of the obvious name constituents in the way one would naively expect. Instead, it comes from the energy of quarks and gluons locked into proton and neutron-bound states by the strong interaction. It sounds almost like a trick answer. The sort of answer a universe gives when it has had several billion years to practice being more subtle than our first guesses. It also changes how one thinks about solidity. The world feels solid and weighty around us. Tables resist, stones press down, bodies occupy space with stubborn conviction. We often imagine that this must be because deep down, matter consists of lots of tiny solid pieces with their own intrinsic heft. But the proton teaches that heft itself can be largely dynamical. The mass is not just sitting there as a passive property of the named ingredients, it is generated by what is going on. That does not make the table less solid. Quite the opposite. It tells us that solidity at our scale depends on a hierarchy of physical structures, and at one important stage in that hierarchy sits the proton, heavy because of intense internal energy. There is another interesting subtlety here. In some familiar bound systems, binding lowers the total mass slightly compared with the simple sum of free parts. Nuclear binding energy works that way in many contexts. Bound nuclei can have slightly less mass than the sum of separate protons and neutrons, because energy is released in forming the bound state. So someone might wonder whether saying the proton mass comes from binding energy is somehow mixing opposite ideas. The answer is that the proton is not just another mild bound system made from already massive free ingredients. The quarks inside it are light, and the strong interaction is so intense that the overall energy content of the confined state is what dominates the mass. One has to treat the proton on its own terms, not as a miniature version of ordinary chemical or mechanical binding. This is one reason everyday analogy becomes dangerous if allowed too much confidence. We can compare the proton to a busy system, a storm, a pattern, a bound state, all of which help a little. But none of those analogies should be mistaken for an actual picture in the old classical sense. The proton mass emerges from a quantum field theoretic reality in which quarks are confined, gluons are self-interacting, and the internal energy budget is enormous. That is a long way from little balls in a little shell. Even the phrase where the proton mass comes from has to be heard properly. It does not mean there is a little location inside the proton where mass is stored like coins in a drawer. It means the origin of the proton mass, in explanatory terms, lies in the total energy of the quark and gluon system. The proton has a mass because the bound state has a certain energy. That energy includes quark motion, gluonic fields, and the whole structure imposed by confinement and quantum chromodynamics. So the source is not a place, it is a physical process, or more precisely a stable physical state defined by ongoing internal dynamics. That is part of why this subject feels so satisfying when one sits with it long enough. It overturns the simple picture, but not in a way that leaves only fog behind. It replaces a crude story with a deeper one. Instead of thinking that the proton is heavy because it contains heavy things, we learn that it is heavy because the strong interaction organizes lighter constituents into a highly energetic bound system. Instead of imagining matter as inert all the way down, we discover that much of the mass in visible matter arises from internal activity. Instead of a passive universe built from tiny pebbles, we get a dynamic universe in which even the ordinary substance of the world owes its weight to invisible quantum motion and interaction. There is also something almost reassuring about the scale of the effect. Nature did not merely hide a subtle correction inside the proton. It hid a profound lesson in plain sight. Every atom around you with a nucleus rich in protons and neutrons is quietly carrying the result of these dynamics. Your own body is full of matter whose mass is largely inherited from the energy of confined quarks and gluons. That is a wonderful thought to end a day with, provided one is the sort of person who finds quantum chromodynamics soothing. Which, if you have come this far, you may well be. And of course the story does not stop at mass. Once physicists realized that the proton was a bound state, whose most obvious constituent masses were not enough to explain its heft, it became natural to ask what else in the proton might have a similarly distributed or surprising origin. How is its momentum shared? How is its spin distributed? How do experiments actually peek into such a busy object in the first place? Those questions follow naturally, because the proton is not a static thing whose properties can be read off from a shortlist. It is a composite system whose observable features emerge from deeper internal structure, and that means the only way to know it properly is to probe it. By now, the proton has become a much stranger object than the tidy schoolbook version most of us first met. It is no longer a simple positive bead resting politely in the nucleus. It is a bound state of quarks, held together by gluons, crowded by a restless internal sea, and made massive not mainly by the bare masses of its valence quarks, but by the energy of the strong interaction itself. At this point, a reasonable person might begin to feel slightly suspicious. This is all very interesting, they might say, but how do we know any of it? If quarks never roam free, if the proton is too small to see directly, if its inner life is governed by quantum rules that resist ordinary pictures, then how exactly do physicists peek inside? What does looking even mean at that scale? The answer is that they do not look in the ordinary sense at all. There is no microscope lens large enough, no beam of visible light fine enough, and no tiny little hatch on the side of the proton that a patient researcher can open with a specialised screwdriver. The methods of everyday seeing fail long before we get anywhere near the proton interior. Instead, physicists use collisions. They fire particles at other particles with enormous energy and examine the patterns that emerge. In the world of particle physics, smashing things together is not a sign of carelessness. It is one of the most precise ways ever invented to learn what matter is made of. That can sound faintly absurd at first. In daily life, if you want to understand how a watch works, smashing it with a hammer is not generally recommended. It will reveal many facts about your temper, and very few about the internal mechanism. Yet at the microscopic scale, collisions are not clumsy destruction. They are a way of probing structure. If you send something small and energetic toward a target and study how it scatters, what angles appear, what energies come out, what new particles are produced, and how momentum is shared, you can infer an enormous amount about what was inside the target. This is especially true when the target is something like a proton, whose internal constituents cannot be separated directly, but do leave measurable signatures when high-energy particles interact with them. There is a broad principle behind this that is worth sitting with for a moment. To investigate smaller structures, you generally need probes associated with shorter wavelengths or higher momentum. Ordinary visible light is far too coarse for the job. It is wonderful for seeing cups, trees, faces, books, rain on windows, and all the things our species evolved to care about, but not for resolving the fine structure of nuclei, let alone the interior of protons. To reach those scales, physicists use particles accelerated to extremely high energies. The higher the energy, the finer the scale that can be explored. It is one of those marvellous features of physics that the act of probing smaller distances requires stepping into more violent-looking regimes. The deeper the question, the harder the collision. This brings us to particle accelerators and colliders, those vast machines that often look in photographs like futuristic plumbing, designed by someone who had lost a wager with geometry. Their purpose is simple to state, even if their engineering is formidable. They accelerate charged particles to very high speeds and then direct them toward targets or toward one another. By controlling the beam energy, the particle type, the collision geometry, and the detectors surrounding the interaction point, physicists can turn impacts into measurements. The proton, despite its familiarity as a constituent of ordinary matter, became one of the great beneficiaries of this approach. Much of what we know about its inner structure was learned by hitting it very hard with other particles and watching what happened. One of the most important techniques in this story is called scattering, and while the word sounds modest, the results have been revolutionary. If a projectile hits a target and bounces off, the pattern of that bounce depends on the target internal structure. This is not peculiar to particle physics. It is true in ordinary life too. Throw a ball at a wall and it behaves one way. Throw it at a curtain and it behaves another. Throw it at a hedge and you will learn something about leaves, branches, and whether your ball is coming back soon. At the subatomic scale, however, scattering becomes far more refined. Instead of observing with eyes, physicists measure angles, energies, cross-sections, final states, and statistical distributions across countless events. The target may be a proton, the projectile may be an electron, a muon, another proton, or some other particle. The resulting data become a kind of encoded report from the proton interior. The use of electrons as probes was especially important because electrons do not participate in the strong interaction the way hadrons do. That makes them cleaner probes in many contexts. If you send an electron toward a proton, the electron interacts mainly through the electromagnetic interaction, and this allows physicists to probe charge distributions and internal structure without immediately drowning in the full messiness of hadron-on-hadron collisions. Earlier scattering experiments had already shown that the proton was not point-like in the naive sense. Its charge was distributed over a finite region. That alone had been enough to undermine the image of the proton as a featureless elementary speck. But as beam energies increased, the story deepened dramatically. The turning point came with deep, inelastic scattering experiments in the later 20th century. The name sounds as though someone in physics decided ordinary words were not alarming enough, but each part means something. Deep means the probe reaches into very small distance scales. Inelastic means the target does not remain intact in the simple way it might in an elastic bounce. Instead, the collision disrupts the proton and produces a more complicated final state. In these experiments, high-energy electrons were fired at protons, and the results revealed something extraordinary. The electrons were scattering in a way that suggested they were hitting point-like constituents inside the proton. This mattered enormously. It was not just a vague hint that the proton had some blurry internal texture. It was evidence that within the proton there were entities behaving as though they were much smaller, more localized constituents carrying fractions of the proton momentum. These constituents were often described at first in language that did not immediately commit to the full quark interpretation, but the connection became increasingly clear. The deep inelastic scattering data were one of the great experimental confirmations that the proton is not elementary. It contains quark-like partons, and the parton picture matured into the quark and gluon framework that now underpins our understanding. It is hard to overstate how elegant this was. Physicists could not take a proton apart like a toy. They could not photograph quarks sitting neatly inside it, yet by scattering electrons off protons at high energy and analysing the debris with exquisite care, they could infer that the proton contained point-like constituents. The proton had been made to reveal itself, not by calm inspection, but by violence disciplined into measurement. Of course, as with all good scientific progress, the answer did not remain simple for very long. The experiments did not merely show that there were 3 quiet quarks sitting inside the proton and nothing more. They showed that the proton momentum was distributed among different kinds of constituents, and as energies rose, gluons became increasingly important. This fit beautifully with quantum chromodynamics, the theory of quarks and gluons. The proton was not just 3 valence quarks in a box. It was a dynamic system in which quarks, gluons, and the quantum sea all contributed to what the probes encountered. Now, electron-proton scattering is only one part of the larger experimental story. Proton-proton collisions have also been enormously revealing, especially at very high energies. When 2 protons collide in a modern collider, the event is not best imagined as 2 little balls bumping into each other in one simple contact. What really matters are the interactions among the proton constituents. Inside each proton are quarks, antiquarks from the sea, and many gluons, all carrying varying fractions of the proton total momentum. When the protons collide at high energy, it is often these constituents that are really doing the interacting. A quark from one proton may scatter off a gluon from the other, or 2 gluons may dominate the interaction, or other combinations may occur. The final state then contains sprays of particles known as jets, leptons, missing energy signatures, resonances, and many other outcomes depending on the process. These collisions are not useful merely because they are energetic. They're useful because the distributions of what comes out encode what was going on inside. If a proton were just a blank positive sphere, the collision patterns would look very different. Instead, the data reveal a partonic interior rich in quark and gluon content. By comparing measured outcomes with theoretical predictions, physicists refine maps of how momentum is shared among the proton constituents. These maps are called Proton distribution functions, and though the name lacks glamour, the idea is profound. They describe the probabilities of finding quarks, antiquarks, and gluons carrying particular fractions of the proton momentum under specified conditions. In other words, they are one of the main ways physicists turn collider data into knowledge about the proton inner population. This is a striking example of how modern science often works. The object of study is too small and too quantum mechanical to picture directly, so one builds statistical and theoretical descriptions that connect measurable events to internal structure. The proton becomes known through repeated interrogation. Not a single glance, but millions upon millions of collisions, each one adding a tiny piece to the portrait. Taken together, these events reveal a stable underlying pattern. The proton is not random. Its inner life follows laws. The challenge is that those laws only show themselves through careful analysis of enormous data sets and equally careful theory. The detectors around colliders are as important to this story as the accelerators themselves. A collision without a detector is just a moment of invisible excitement followed by missed opportunity. Modern particle detectors are layered instruments designed to record the tracks, energies, momenta, and identities of outgoing particles as comprehensively as possible. Charged particles curve in magnetic fields, allowing momentum measurements. Calorimeters absorb particles and measure their energy. Specialized systems identify muons or distinguish electrons from hadrons. The detector becomes, in effect, a giant sensory organ wrapped around the collision point, turning ephemeral events into analyzable records. What makes this particularly beautiful is that no single event tells the whole truth. A proton collision is a single toss of the quantum dice within strict physical rules. One event may produce one pattern, another a different one. It is only through collecting vast numbers of events and understanding the probabilities that the proton inner structure becomes legible. Physics here is less like reading a sentence and more like learning a language by listening to millions of conversations. Patterns emerge, rare processes become visible, background noise is separated from genuine signal. The proton, stubbornly inaccessible to direct inspection, becomes knowable through statistics, symmetry, and persistence. There is a certain irony in the scale of the machinery involved. To learn about one of the tiniest components of ordinary matter, humans have built some of the largest and most complicated scientific instruments in history. Rings many kilometers around, magnets colder than deep space, data systems that handle extraordinary volumes of information, international collaborations involving thousands of people. All of that effort in part to ask the proton what it is made of and how its constituents behave. One could take this as evidence that nature is not especially keen to surrender its secrets cheaply. One could also take it as evidence that human curiosity is very hard to discourage once properly motivated. Different colliders and fixed target experiments have each contributed their own part to the proton story. Some experiments were designed primarily to discover new particles. Others focused more directly on hadron structure. Electron-proton facilities have been especially valuable because of the relative cleanliness of the probe. Proton-proton colliders, meanwhile, reach astonishing energies and provide insight into the gluon-rich regime of the proton. Heavy ion facilities, although often aimed at studying matter under extreme conditions, also deepen understanding of strong interaction physics more generally. The field is cumulative. No single machine solved the proton. Instead, generation after generation of experiments peeled back more of the picture. One of the great practical difficulties is that the strong interaction behaves differently depending on the scale. At very high energies and short distances, some calculations become more tractable, and quarks and gluons can be treated in ways that make perturbative methods useful. At lower energies, Where confinement dominates bound states like the proton, calculations become much harder. This means that colliders are especially powerful not only because they produce spectacular events, but because they let physicists probe regimes where the partonic structure becomes experimentally visible. The proton can be struck hard enough that its inner constituents reveal themselves through the final state, even though those constituents never emerge as free quarks in isolation. This point is crucial. Colliders do not let physicists open the proton and pour its contents onto a tray. Confinement still rules. What they do instead is create conditions under which the underlying quark and gluon structure governs what the detectors see. The final products are hadrons, leptons, photons, and other allowed particles, not free quarks sitting alone. Yet the detailed shapes of jets, the scattering rates, the angular distributions, the momentum transfers, all of these are fingerprints of the partonic substructure. The proton does not reveal its insides by surrendering detached pieces. It reveals them by the patterns produced when it is struck hard enough. This is a lovely example of indirect realism in science. We often do not observe the most fundamental things in the same way. We observe chairs or moonlight or puddles after rain. We observe their effects, their constraints, the traces they leave in other measurable things. This does not weaken the science. On the contrary, where many different lines of evidence converge, the unseen structure becomes more secure, not less. The proton inner world is one of the best supported examples of that kind of knowledge. It is not seen directly with eyes, but it is probed, mapped, constrained, modelled, and confirmed in ways that make the old simple picture feel almost quaint. Even the word peek in the title has a kind of polite understatement to it. Physicists do not peek inside protons the way one peeks into an oven. They interrogate them with breathtaking energy and then interpret the aftermath with great mathematical care. Yet the word still fits in spirit because there is something almost intimate about it. After all the machinery, all the engineering, all the statistical analysis, the goal remains simple in essence: to learn what is in there, to understand how a familiar particle gets to be what it is, to find out how the visible world builds itself from hidden structure. There are also newer and more refined ambitions in this area. Physicists do not merely want average descriptions of how momentum is shared. They want richer maps of the proton, including spatial information, correlations, and three-dimensional structure in momentum space. They want to understand how the proton spin is built from the spins and orbital motion of quarks and gluons. They want more precise information about the C-quark content in the gluon-dominated regions. Future and proposed facilities have been designed partly with these goals in mind, because even after decades of experiments, the proton is not a finished subject. It is familiar, yes, but still full of work for science to do. That may be the most appealing thing about the proton from the perspective of quiet curiosity. It is both understood and not finished. We know enough to say with confidence that it is a composite particle made of quarks and gluons. We know enough to explain why the old picture of a featureless positive speck is inadequate. We know enough to calculate and predict a vast array of processes involving its constituents, and yet there remain open questions about the detailed sharing of spin, the behaviour of gluons in certain regimes, the fine structure of the sea, and the best ways to connect theory and experiment at every scale. The proton is not a mystery because we know nothing about it. It is a mystery because what we know has revealed further depths, and that is what colliders have made possible. They have turned the proton from a simple nuclear resident into a measurable quantum world. By accelerating particles to astonishing energies, and by building detectors capable of reading the wreckage with exquisite precision, physicists have learned to probe the proton far beyond the reach of direct sight. They have shown that its interior is populated by quarks, antiquarks, and gluons. They have measured how momentum is shared. They have confirmed that confinement governs what can and cannot emerge. They have turned impacts into understanding. The proton, once just a label in atomic diagrams, has become a deeply studied object whose internal complexity is mapped through collisions. And once you appreciate that, another shift begins to happen in how the proton is imagined. It stops being a tiny container with a few objects inside and starts looking more like a constantly changing cloud of probability, momentum, and interaction. One whose identity is stable, but whose interior is better described in terms of distributed activity than tidy classical placement. After everything we have uncovered so far, it becomes harder and harder to keep the proton in the old mental frame of a tiny object with a tidy interior. By the time quarks, gluons, the sea, confinement, dynamically generated mass, and collider evidence have all had their say, the proton begins to look less like a miniature bead and more like a distributed quantum system. That does not mean it becomes vague in the sense of being unreal or unknowable. Quite the opposite. It means that the most accurate way to picture it is no longer as a compact little pellet, but as a shifting cloud of constituents, momentum, energy, and probability, whose overall identity remains stable even while its internal details are in constant motion. That is one of the hardest transitions for the imagination to make, because our minds like objects better than clouds. Objects are tidy. They have edges. They sit in places. They keep themselves together in a way that reassures the part of the brain that wants the world to behave like furniture. Clouds, by contrast, are distributed. Their boundaries are less sharp. Their interior is not made of a few countable pieces resting in assigned seats. A cloud is a pattern, a spread, a changing arrangement with persistence but not rigidity. In daily life, if you ask where a chair is, the answer can be quite precise. If you ask where a cloud is, the answer is broader and more conditional. The proton, at the deepest useful level, belongs more to the second category than the first. Of course, like any comparison, this one must be handled with care. The proton is not literally a cloud in the meteorological sense. It is not made of droplets drifting over a quantum countryside, but the cloud idea helps because it emphasizes distribution and motion instead of fixed tiny architecture. The proton is a cloud of probability amplitudes, quark content, gluon activity, and momentum sharing. The valence quarks are part of that cloud. The sea quarks are part of that cloud. The gluons are an enormous part of that cloud, and all of them contribute to a physical object that behaves as a single proton when viewed from the outside. That last point matters. The proton is not becoming less real because its internal description becomes more spread out and dynamic. It remains one of the most stable and well-defined particles in ordinary matter. It carries a fixed positive charge. It has a measurable mass. It has spin. It participates in atomic nuclei in dependable ways. Chemistry and nuclear structure rely on it. So we must hold two truths at once. Externally, the proton is a robust particle with consistent properties. Internally, it is a shifting quantum cloud whose constituents do not sit in fixed classical positions. The challenge is not that one of those statements cancels the other. The challenge is that everyday intuition prefers not to hold both at once. One reason this cloud picture becomes necessary is that the proton is described by quantum mechanics, and quantum mechanics does not assign little classical trajectories and fixed locations to its constituents in the way ordinary imagination wants. When people first hear that quarks are inside the proton, they naturally want to know where they are. Are they near the centre? Are they orbiting? Are they spaced evenly? Are they in corners, if such a thing could even make sense at that scale? But these questions borrow too much from the language of ordinary objects. In the quantum description, what is meaningful is not a little map with pinned positions. What is meaningful are probability distributions, momentum distributions, field configurations, and the outcomes of measurements under specific conditions. That is why the proton often appears in modern descriptions not as a fixed arrangement, but as a state. A quantum state is not a static photograph. It is a structured set of possibilities and relationships. If that sounds like the language has grown annoyingly careful, that is because reality at this scale forces it to. The proton is not simply a thing with contents. It is a bound quantum system whose measurable properties emerge from the distribution and interaction of those contents. To say it is cloud-like is to admit that the best description is spread out and dynamic, not tiny and rigid. There is something deeply revealing in the way physicists talk about the proton in different experimental contexts. In one experiment, attention may focus on how the proton charge is distributed. In another, on how momentum is distributed among quarks and gluons. In another, on the spin content and angular momentum contributions of its internal constituents. In another, on generalized distributions that combine momentum and spatial information in more sophisticated ways. The fact that all these different maps are useful tells you something important. There is no single simple picture of the proton interior that captures everything at once in the way a cross-section drawing of a machine might. Different experimental questions reveal different aspects of the same bound quantum cloud. That can feel unsatisfying if one is hunting for a final image. We like our scientific understanding to culminate in a clear drawing, the sort one could place in a textbook and feel that the issue has been settled. Yet some parts of physics do not end in a drawing. They end in a framework. The proton is one of those cases. We know a great deal about it, but what we know is encoded in mathematical descriptions, distribution functions, lattice calculations, scattering amplitudes, and experimental reconstructions, not in a single cartoon with all the truth squeezed into one neat diagram. The diagrams remain useful as introductions, but the proton itself outgrows them. This does not mean the proton is formless. It has structure, it has a measurable size, it has internal correlations, but its structure is not like the inside of a watch. If you opened a watch, you would expect to see pieces with clear identities and positions. If one could somehow open a proton, which is not an operation nature especially allows in any everyday sense, one would not find 3 tiny hard nuggets frozen in place among little packets of glue. One would find a quantum field theoretic reality in which quarks and gluons are distributed, interacting and fluctuating. The proton identity would be there, but not in the form classical intuition prefers. One of the most useful consequences of the cloud picture is that it helps explain why collider experiments reveal different proton contents depending on the energy scale and the kind of process involved. If the proton were just a simple 3-body object, then all sufficiently smart experiments would merely keep rediscovering the same 3 ingredients in the same straightforward way. But because the proton is a dynamic cloud, what a given probe encounters depends on how deeply it probes, how much momentum transfer is involved, and what aspect of the proton state is being measured. Sometimes the valence quarks dominate the story. Sometimes gluons dominate. Sometimes the C becomes especially important. The proton is one object, but it is an object whose inner description is rich enough that different questions illuminate different regions of the cloud. This is especially clear when one thinks about gluons. In simpler introductory accounts, gluons are often presented as though they are just exchange particles shuttling between the valence quarks. That is not entirely wrong, but it encourages the image of a basically sparse interior with a few messages passing back and forth. The cloud picture corrects that. Gluons are not occasional messengers crossing an otherwise empty room. They are a major part of the room. They carry a large share of the proton momentum. They contribute centrally to its mass. They generate the C. They interact among themselves. So the proton as a cloud is not mainly a cloud of 3 quarks with some light background decoration. It is a gluon-rich system in which the quarks themselves are embedded in a much broader field structure. That realization is one of the reasons the proton can feel almost more like weather than like machinery. Not because it lacks order, but because its order is distributed and dynamic. Weather has structure, pressure systems, fronts, currents, predictable ranges of behavior, and measurable patterns. Yet it is not built from a few obvious mechanical pieces locked together. The proton is similar in that its identity is robust while its internal content is in continual motion. Once again, the analogy should not become too proud of itself, but it serves its purpose. It reminds us that the deepest physical reality may be organized without being static. Another virtue of the cloud picture is that it softens the misleading question of where exactly is each quark right now. In the classical world, that would be a reasonable question. In the Proton, it is too blunt. Quantum entities are described by states and distributions. Their measurable behavior depends on interactions and observation conditions. Asking for fixed positions independent of all that is rather like asking where exactly the melody sits inside a song. The melody is real, but the question has to be posed in the right terms. So too with quarks and gluons. Their reality inside the proton is not in doubt, but their reality is distributed, relational, and tied to the formalism of quantum theory. This is also why the proton can carry stable overall properties despite the shifting character of its interior. A cloud can have a stable overall form for a while, even though the droplets within it move. A river can keep its path while the water changes. A city can remain the same city while the people, traffic, deliveries and weather vary from hour to hour. The proton, at the quantum level, has something of that sort of persistence. Its global features remain fixed, its charge remains what it is, its mass remains what it is, its spin remains what it is. Yet the detailed sharing of momentum and internal activity among quarks and gluons is constantly alive. That dynamic character becomes even more interesting when one considers the proton spin, a quantity that sounds at first like it should be easy to account for. One might naively suppose that if the proton is made of quarks, then its spin should simply come from the spins of those quarks added together in an obvious way, but experiments show that this expectation was far too simple. Only part of the proton spin comes directly from quark spin. The rest must involve gluon spin and the orbital motion of quarks and gluons within the proton. Once again, the cloud picture is more faithful than the bead picture. The proton properties emerge from the whole moving system, not just from a tiny list of static ingredients. There is something almost educationally mischievous about the proton in this respect. At every stage where a student or a casual reader might hope for a simple accounting, the proton gently says not quite. What gives it mass? Not just the bare quark masses. What gives it spin? Not just the valence quark spins. What is inside it? Not just 3 fixed points. How should it be pictured? Not as a tiny solid object. This does not make the proton obscure in a hopeless sense. It makes it mature as a scientific object. It resists simplification because reality at that level is richer than the simplified stories that first introduce it. And yet, even while resisting classical pictures, the proton remains wonderfully empirical. This is not the kind of cloud one invents because one has given up on precision. It is the kind of cloud forced on us by precision. The distributions are measured, the models are tested, the pattern functions are extracted from data, the generalized pictures are constrained by experiments. Lattice methods and theory build on the same structure. The proton as a cloud is not a poetic surrender. It is the result of physics becoming more exact than ordinary language is comfortable with. That distinction is important because cloud language can sometimes make people think of vagueness, in the sloppy sense, as though nothing is definite anymore. But many things can be distributed without being vague. A sound field in a concert hall is distributed. A weather map is distributed. The charge distribution in an atom is distributed. These are not failures of knowledge. They are the proper way to describe systems whose reality is not concentrated into one neat classical point. The proton belongs in that category. Its cloud-like character is not a confession of ignorance. It is a more accurate form of understanding. It also tells us something broader about matter itself. The visible world is built from objects that feel stable and bounded to us. We sit in chairs, lean on walls, hold cups, and walk on floors that all seem to have simple material integrity. But underneath that ordinary stability lies a hierarchy of deeper structures, and at the level of the proton, those structures are not rigid grains. They are bound quantum clouds. So one of the hidden foundations of everyday solidity is not solidity in the old little pebble sense at all. It is distributed field behavior stabilized into durable particles. That is an astonishing thought once it has had time to settle. There is also a kind of quiet humility in it. Human intuition evolved for survival among medium-sized objects moving at ordinary speeds. It was never designed to visualize confined quarks and gluon distributions. The fact that our first mental pictures fail is not embarrassing. It is almost inevitable. What matters is that physics gives us better pictures, even when those pictures are not pictures in the usual visual sense. The proton as a living shifting cloud is one of those better pictures. It is not the last word in formal detail, but it is much closer to the truth than the old idea of a simple positive nugget. And perhaps living is the right word to use here, provided we keep it within limits. Not living as in biological metabolism, growth, memory, or desire. The proton is not plotting anything. It is not feeling underappreciated by chemistry textbooks, but living in the sense that its interior is active, not frozen. There is motion, exchange, fluctuation, orbital behavior, field energy, and a continual redistribution beneath a stable outward identity. The proton is not dead structure, it is stable activity. That is why the cloud picture helps. It lets us think of the proton as something whose being consists in organized ongoing internal motion, rather than static assembly. By the time one fully accepts that, the original question of what a proton is really made of has changed its flavor. It no longer sounds like a request for a simple list. It sounds like a request for a layered explanation. Yes, it involves quarks. Yes, it involves gluons. Yes, it involves the sea. Yes, it involves confinement and dynamic mass generation. But beyond all that, it involves a new way of thinking about what a thing is. The proton is not just made of ingredients, it is made of a structured quantum state, one that appears particle-like and stable from the outside while remaining internally cloud-like and dynamic. That is a difficult idea to carry all at once, but it is also one of the most rewarding. It means the proton is not merely one more object in the universe. It is a lesson in how the universe builds objects in the first place. Not always by stacking hard bits, but by organizing fields, energy, and interaction into stable patterns that can persist, combine, and eventually become part of atoms, molecules, planets, and people. Once you see the proton that way, it becomes less of a tiny mystery hidden in the nucleus, and more of a quiet demonstration that matter itself is subtler than ordinary intuition ever guessed. And from there, the final step is almost unavoidable, because once the proton has shifted from a little positive speck to a bound quantum cloud, the question is no longer only what it contains. The question becomes what kind of thing it actually is in the deepest useful sense, and why that matters for how we understand the physical world at all. So after all of this, after the old picture has been taken apart and the newer one has grown steadily more complicated, we can finally come back to the question in its simplest form and ask it properly. What is a proton really? The most honest answer is that a proton is not a tiny solid object, not a final indivisible bead of matter, and not merely a little box with 3 smaller particles rattling around inside. A proton is a stable bound state of the strong interaction. It is a quantum object made from quarks and gluons, held together by confinement, filled with ongoing internal motion, and given most of its mass by the energy of that internal structure, rather than by the bare masses of its defining quarks alone. That is the answer in modern physics terms, and it is already very far from the tidy classroom dot most of us first met. Yet that answer is not just more complicated, it is better. It tells us more clearly what kind of thing the proton is, and it helps explain why this seemingly humble particle matters so much. When people first hear that a proton is made of quarks, there is a tendency to treat that as the finish line. Fine, they say, so the proton is really just 3 quarks. Mystery solved. But as we have seen, that is only the front door of the subject. The proton has 2 up quarks and 1 down quark in the valence sense, yes. Those quarks help define its identity, including its positive charge. but they do not exist as little isolated marbles inside a shell. They are confined. They are embedded in a rich gluon field. They are accompanied by a sea of transient quark and antiquark pairs. Their motion matters, the gluons matter, the sea matters, the shared momentum matters, the collective energy matters. The proton is not the sum of 3 labelled pieces in quiet storage. It is a self-consistent physical state in which all of these ingredients participate at once. This is one reason the phrase "what it is made of" can be slightly misleading if taken too literally. In daily life, to be made of something usually means the parts are more basic than the whole and can be separated from it without changing what they are. Wood exists before and after the chair. Flour exists before and after the loaf. Metal exists before and after the watch spring. But the proton is not built in that ordinary way. The quarks inside it are real, but they do not appear as free particles outside hadrons. The gluons are real, but they are not just passive connectors in the background. The proton is therefore not best understood as a container holding detachable ingredients. It is better understood as a bound pattern allowed by the laws of quantum chromodynamics. That phrase may sound technical, but the idea behind it is straightforward. Nature permits certain stable arrangements of quarks and gluons under the strong interaction. The proton is one of those arrangements and one of the most important. It is stable, durable, and common. It is not fundamental in the way an electron is treated as fundamental in the standard framework, but it is foundational in the architecture of visible matter. That is a crucial distinction. The proton is not elementary, yet the world we know depends on it. And that brings us to the second half of the question, the part that asks why it matters. The proton matters first because it sits very near the centre of ordinary matter, both literally and conceptually. Atomic nuclei are built from protons and neutrons. The number of protons in a nucleus determines what element an atom is. Change that number, and you change the identity of the atom itself. 1 proton, and you have hydrogen. 6, and you have carbon. 8, and you have oxygen. 26, and you have iron. 79, and you have gold. That means the proton is not just one constituent among many. It is one of the main markers of physical identity in the material world. A great deal of chemistry, biology, and everyday substance rests on proton count. That alone would make the proton important, but the story goes further. The proton also matters because much of the mass in visible matter comes through particles like protons and neutrons. Atoms are mostly empty space in the old rough sense, yet most of their mass resides in the nucleus, and much of that nuclear mass comes from protons and neutrons. So if you ask why the ordinary world has weight, why stones feel substantial, why your own body has mass, why the material universe is not merely a delicate haze of electron behaviour, the proton enters the answer in a very direct way. And then the story becomes even better, because once the proton enters that answer, it brings with it one of the deepest lessons in modern physics. The proton mass does not come mainly from the bare masses of its valence quarks. Most of it comes from the energy of the strong interaction, from quark motion, gluon fields, and confinement inside the bound state. So the proton matters not only because it contributes mass to visible matter, but because it teaches us what mass in visible matter really means. Much of the heft of the ordinary world is dynamically generated. Matter is substantial, not just because it contains tiny heavy ingredients, but because nature organises energy into stable composite particles. That is a remarkable fact once it settles in. The familiar world is not built from tiny hard grains that simply carry all their weight from the start. It is built to a significant extent from energetic quantum structures whose internal dynamics generate much of what we experience as ordinary material mass. The proton is one of the clearest examples of that principle. It turns an abstract truth about mass and energy into something concrete enough to sit at the heart of atoms. The proton also matters because it marks one of the places where human intuition has had to change most dramatically. In the older mechanical picture of matter, The hope was always that if one kept going smaller, one would eventually reach simple little pieces, each with its own straightforward identity, each behaving like a reduced version of familiar objects. The proton looked for a while like it might be one of those pieces. Instead, it turned out to be something much more interesting. It is a quantum cloud-like bound state, whose constituents cannot be isolated, whose mass is largely dynamic, and whose internal structure is revealed not by opening it like a box, but by probing it through high-energy collisions and careful theory. That change in perspective matters because it teaches a broader lesson about how physics works. Deeper understanding is not always a matter of smaller and smaller billiard balls. Sometimes it is a matter of fields, symmetries, allowed states, and emergent structure. The proton teaches exactly that. It shows that a thing can be real, stable, and indispensable while also being internally dynamic and conceptually richer than our early pictures allowed. In that sense, the proton is not just an object of study. It is a corrective to a whole style of naive materialism. There is also something philosophically satisfying about where the proton leaves us. If you start with the question, what is matter made of? The proton first looks like a reassuring answer. Then it stops being reassuring. Then it becomes reassuring again, but on a deeper level. Not because it is simple, but because it fits into a coherent and testable theory. The Quark model explains hadron families. Quantum chromodynamics explains the strong interaction. Scattering experiments reveal point-like constituents. Collider data map momentum sharing. Lattice methods support the picture quantitatively. The proton is not a mystery because science failed to reach it. It is a mystery that science reached and then found richer than expected. That richness matters culturally as well as scientifically. Human beings have always wanted to know what the world is made of. Ancient philosophers proposed elements. Later thinkers proposed atoms. Modern physics uncovered nuclei, electrons, quarks, and fields. The proton sits in the middle of that long history. It belongs to the ordinary world and to the deepest modern theory at the same time. It is part of the air of ancient stars, the chemistry of planets, the structure of living things, and the equations of high-energy physics. Few objects carry that kind of double citizenship so well. The proton is both a resident of daily matter and a guide to the deepest levels of current physical thought. It also matters because it reminds us that stability and simplicity are not the same thing. A proton is stable, very stable. It persists across immense spans of time in ordinary matter. One could almost call it dependable if particles had personalities and schedules. Yet its stability does not come from being simple in the old elementary sense. It comes from the very structure of the strong interaction. It comes from confinement. It comes from the way quarks and gluons are allowed to organize themselves into bound states. That is an important lesson. The world is full of durable things whose durability is not a sign of inner emptiness but of inner structure done well. In a way, that makes the proton feel less like a little object and more like a successful solution. Nature has certain rules. Given those rules, the proton is one of the stable outcomes that can exist. It is a durable pattern in the strong interaction, one that goes on to make nuclei possible, and, through them, atoms and chemistry, and all the familiar matter around us. That idea may be less visually satisfying than a tiny hard sphere, but it is much more powerful. It lets us see the proton not as a miniature pebble, but as a physical achievement of the universe itself. There is another reason the proton matters, and it has to do with unfinished science. For all we know about it, the proton is not a completed topic. Physicists are still refining their understanding of how its spin is distributed among quark spin, gluon spin, and orbital motion. They are still improving maps of its internal structure. They are still studying the role of gluons in different momentum regimes. They are still testing theory against ever more precise experimental data. So the proton matters not only as something already understood, but as something still active in research. It is one of those rare subjects that can appear in an introductory diagram and in the cutting edge of high-energy physics without embarrassment. That makes it especially satisfying as a scientific object. Some things are important but mostly settled. Some things are exciting but quite remote from ordinary matter. The proton is both fundamental to the visible world and still rich with open detail. It has the right kind of depth. The deeper you go, the more it rewards attention. That is not because it becomes less real. It is because it becomes more fully itself. One could even say that the proton matters because it helps connect scales that human thought tends to separate. On one side there is the very small, the quantum world of quarks, gluons and fields. On the other, there is the ordinary world of substance, chemistry, mass and material objects. The proton sits between them. It translates the strong interaction into the architecture of matter. It takes quark and gluon dynamics and turns them into something stable enough to anchor nuclei. Without that bridge, the world would not build upward in the same way, so the proton is not merely one more item in the particle catalogue. It is one of the places where the microscopic becomes the ordinary. That is why asking what a proton really is turns out to be such a good question. It begins innocently, as though one were asking for the next smaller piece in a nesting doll of matter. But the answer changes the meaning of the question itself. The proton is not really a smaller piece in that naive sense. It is a composite quantum state. It is a dynamic cloud. It is a confined arrangement of quarks and gluons. It is a major source of visible mass. It is a stable resident of nuclei. It is a demonstration that matter is made not only of ingredients, but of interaction and energy structured into durable form. And perhaps that is the best place to leave it, with the proton no longer looking simple, yet looking more meaningful because of that. We started with the kind of particle most people think they already know. A proton, positive charge, centre of the atom, basic building block, end of story. What we found instead was a hidden interior full of motion, binding, fluctuation, and distributed structure. We found quarks that cannot be freed, gluons that do far more than hold things together quietly, a sea that churns beneath the proton's stable identity, and a mass that comes largely from energy rather than from the bare masses of the named constituents. We found that one of the most ordinary particles in the universe is anything but dull when looked at closely. And now here you are, a little farther along in your own evening or night than when we began, carrying around the fact that every ordinary atomic nucleus owes something to one of the strangest and most successful bound states in physics. That is one of the pleasures of questions like this. They begin with something familiar, then slowly make the familiar feel deeper without making it less real. The proton is still there in matter, still doing its quiet work, still helping define the elements and the mass of the visible world. But it is no longer just a positive speck in a diagram. It is a reminder that even the plainest ingredients of reality may have far more going on inside than first impressions ever suggest. So if someone asks what a proton really is, the gentlest honest answer might be this. It is one of the ways the universe turns energy, interaction, and quantum structure into stable matter. And if they ask why that matters, the answer is equally simple. Because without that, there is no ordinary world in the form we know, no nuclei built this way, no chemistry quite this way, no visible matter with the same mass and structure, and no easy reason for our own little corner of reality to feel as solid and dependable as it does. Which is not a bad thing to sit with for a moment, especially late in the day. One small particle, common enough to hide in plain sight, and deep enough to contain half a century of modern physics inside its quiet existence.